Good morning, everyone, and welcome to Innovation Management for AI. What I'm noticing is that we have far more students online than here on campus. It's fine, it's a hybrid setting. But if you're in Deggendorf today, please come on campus and follow the lecture here from campus, because the hybrid setting is mainly intended for those who are currently doing their internship far away. So if you live nearby, just come on campus. It will be more fun to have this discussion. And welcome also to those on campus. It's good to see you all here. And we will also have some guest lectures today in the afternoon, as well as 2 guest lectures tomorrow. So it would be cool if you're here on campus, and I think will be a good sign also to our visitors giving their guest lectures. In this lecture for this weekend and some of the following weekends, what I want to discuss with you is not how you can build prototypes. You have learned this in plenty of AI lectures, how you build AI prototypes. What I want to discuss with you is how you can make money out of these prototypes. So how you can commercialize all of this. And for this, we will look a little bit first at some historic promises of AI and some of the failures of the past. Then we will look at the current deep learning era, some things that work, some things that don't work. And then we'll see how we can do an AI transformation of a company. We'll look at current challenges. There are lots of them recently. There have been more and more legal challenges in the last few years when it comes to deploying AI and making money out of AI. We will look at them. And that's the content for this weekend, so today and tomorrow. And then you'll be working on a case study, which are the presentations in the following weekends that I'll talk about. But I'll say more about the organization in a few minutes. Who of you, so the ones here on campus, as well as the ones who are in Zoom, are currently doing an internship? Okay, because this course is offered as a mandatory course to those who are currently doing their mandatory internship. The course can be taken by others as well. So online, maybe just raise your hand or thumbs up if you're doing an internship right now. And here in the room, maybe just raise your hand again. So some of them. I know some may have finished their internship already or doing it in the future, or they're not doing an internship. That's totally fine. And who of you is from one of our AI undergraduate programs, either the German or the English language one? Maybe again, raise your hand. Okay. And online, there will be more students who are probably not in those programs, because this course is also offered as an elective as well as to our exchange students. So if you are in one of the AI undergrad programs, either the German language one or the English language one, you have taken lots of AI courses so far, like AI programming, assistance systems, computational logic, computer vision, the introduction to AI, machine learning, and natural language processing. Has any one of you taken all of them already, or most? But they all should be taken, at least if you follow the regular schedule before the internship. For example, I have taught the computer vision course. And the computer vision course is highly technical, and so are probably most of those other courses as well. And what you learn in those courses, you learn lots of maths, lots of theory, lots of coding, and you will build prototypes. And when you do your internship, you will also build such prototypes. But the question is, how do I finally make money out of them? Because eventually you work for a company and you need to deliver a positive return on investment. And that's something we will discuss. And overall in the news, AI looks really promising. There are lots of promising news and papers, lots of news about AI. But I want to discuss with you what can go wrong in reality. Maybe some other news you have heard, or maybe you have seen something yourself during the internship. So maybe you want to be sharing some of your insights. What can go wrong aside from all these positive news? And there's a question here in the chat. If all of this is being recorded, yes, the lecture part today and tomorrow will be recorded and it will appear on YouTube. But my hope is that you're still staying in the live session and that you come on campus if you're nearby. So just don't sit in your student residence in Deggendorf. Maybe just open the Zoom app on your phone and walk here to follow this. So what can go wrong in reality? Anyone wants to share some insights? Have you raised your hand? Okay, so we got some comments here in the chat. So one student says, Amazon biased recruiting algorithms, or a biased algorithm that led to maybe suboptimal outcomes as well as negative news. Yes, one failure. So if you have any other, say, news or insights when AI goes wrong, maybe the AI led to bad outcomes, maybe the prototype didn't finally work and couldn't be put in production, whatever you want to share, this is your opportunity. For those of you doing your internship, what have you noticed? Are companies all happy with AI, or what doesn't work out? Because plenty of you also here in the room raised their hand that you're currently doing your internship. So what has not worked out with regards to AI? Bias in results. Yes, that's also one of the comments here in the chat. Yes? Okay. So you couldn't access the data, or what?
You can't be sure as a company, or at least the company says we can't be sure where the data is going at the end.
Okay. Yeah, so one of the concerns is you don't want to send all your data to the cloud, right? So you could run your own large language model and maybe have full control over that. But yeah, don't put all your trade secrets in ChatGPT. ChatGPT offers that you can get this team version or something like this, for which they give you more guarantees. Whether they eventually honor those rules or not is a different question. But yeah, so data privacy issues, trade secret issues, very important. And lots of comments here in the chat. One student says hallucinations in LLM responses. One student says CV screening done by AI seems to skip you most of the time. Could happen. Maybe because of a biased algorithm. Some people are worried that an AI would do their job and they lose their work. Someone says people with no AI background, they overestimate what generative AI could do. One big challenge is to stay up to date with AI because the field is moving very rapidly. And one person says, instead of doing something interesting, you just end up collecting and annotating data because the existing AI solutions are way better than something you can build from ground up. Yeah, may happen. And ethical concerns. So lots of insights from you. And usually these courses that accompany the internship, they are either always before or after the internship, as you have probably noticed. But there's a clear reason why this course is during your internship, because I want you to already have some real-world experience so you can contribute to the discussions, but I also want you to have enough time to actually take advantage of what you have learned here. And that's why this course takes place during the internship, and that's why it's multiple weekends. So ethical concerns, lack of context, you could create fake images or news that can have political impact. Lots of insights, so thank you. There are some other news that don't sound that positive. So when you look at the news on the internet or in newspapers, it looks like, yeah, AI will solve all your problems and it's all magic and it works. But there are various studies that say that, yeah, lots of companies, the large majority of companies see AI as a huge opportunity, but only a few of them, just a small proportion, have actually extensively incorporated AI in their processes or products. So R&D and deployment is something they lack on. There are other news that say like 80% of AI projects fail or don't get off the ground due to various reasons, for example, a lack of data. And there are some other numbers that say that 80% of organizations don't understand the data required for AI. So a lot of them want to do AI, but they struggle with them. And there are more issues, like you mentioned. Maybe you have your data, but you have great models in the cloud, but you don't want to be sending all your trade secrets to OpenAI, which I totally understand. There are some other numbers I collected, and they all go into the same direction. They say something like 85% of all AI projects would not impress CIOs. What's a CIO? What does that acronym stand for? Usually Chief Information Officer. Sometimes could be Chief Innovation Officer, but I think in that context, typically Chief Information Officer, the IT boss in a company. So that doesn't look very positive. And I also have some timeline here of news that I found on the internet. And it's something like in 2016, Gartner reported that 60% of data science projects fail. Then Gartner reported just the following year that the fail rate on data science projects is closer to 85%. And then VentureBeat reported 2 years later that 87% of data science and machine learning efforts fail and never impact business. Looks like dramatic numbers, and they're even going up. Does anyone have an idea why this proportion seems to get even worse over time? And probably by now, we're at far more than 90%. Yeah. And there are probably not enough experts to do all of this. So, and probably the fail rate is far more than 90% now. Yes, because there's this huge AI hype and everyone wants to do AI. And a lot of that doesn't seem to work out very well. And whatever comments you have in for the ones taking this course online, feel free to send this in the chat. One student says, because more and more people are there who can do some AI, but without the proper background knowledge. Yes, that's true. We'll look at some of that as well in this course. And there was another very famous Twitter or X post a few years ago. And that person said something like, as a rule of thumb, you can expect the transition of your enterprise company to machine learning will be about 100 times harder than your transition to mobile. And a lot of big corporate are still struggling to fully offer all their internal services on mobile, still today. Now we see this transition is probably much tougher. And there's also something that is often called AI washing, that everything now seems to be AI. But if you just look under the hood, it's fairly trivial stuff. Like maybe just a few rules, and then it's called a big AI. I guess you've seen this too. So remember this term AI washing. And there are obviously a lot of consultants around AI who try to cash in and have created a certain hype, but often lack an understanding. There's something here like a businessman, buys fruit like bananas and sells it for €2. If an entrepreneur would turn this into juice, sells it for $4, and a consultant will give you a presentation about how to turn bananas into a juice and charge $200. So consulting is important, and some of you will obviously be working in consulting once you graduate. Is any one of you doing an internship in consulting, for example? If there's anyone online doing an internship in consulting, maybe raise your hand. There's at least one person or multiple. So consulting is very important in order to help other companies getting into AI and turning AI into money. But obviously, there's also lots of consultants who just sell some slides eventually about business problems or give presentations that are completely useless. Yeah, so I've just checked the comment section. And what I always like to do in the beginning of my lectures is something that I call the map of computer science. So this map here I found a few years ago on the internet, and it tries to visualize the field of computer science in total. And then I always highlight what we actually look at in a specific course. In this course, we just focus into a smaller area. We will look obviously in AI because it's called innovation management for AI, but we also look at concrete applications and how to make money out of them. So the goals of this course are, I want you to understand the business potentials and how to commercialize AI so that you can add values in companies. We will look at typical obstacles and why AI projects fail. We will look at how we can solve some of these obstacles, and we'll see how we can manage innovations and how we can successfully implement AI. What I also feel, that term innovation management can mean lots of different stuff. To some people, it means something like how to detect innovations early and how to accompany them. But in this course, it more means that we want to add concrete value using AI and make sure that AI eventually adds money to companies. Since most of you are from the AI undergrad programs, you already possess lots of knowledge in how to build AI. So there will be some technical stuff in this course, but you have lots of technical knowledge already. So in this course, we will also largely look at management issues and what you need to look at in order to make money out of AI. This is an intensive course of 3 days. And in the past, it was really 3 days. But now it's 2 days of lectures and multiple days for presentations, because we're just so happy to have all of you studying here. And our AI programs keep receiving thousands of applications every year. So we are unable to do all the presentations on a single day. And this course carries 3 credit points. And today and tomorrow, we will have lectures. And then you need to pick a case study, any case study you wish to have, about more like a business-related problem around AI. Maybe how to do a certain AI project of your choice or at the company where you're doing your internship, and obstacles you may face, maybe from a legal perspective, from a budget perspective, from an HR perspective, whatever. Or from a holistic view, you could also look at an entire AI transformation of a company and what typical issues could be. So you're very free in this, and you need to present this eventually in groups of 3 to 4 students. You will give a 15-minute presentation, and there will be a Q&A, and you can only pass or fail this course because the study regulations of the AI undergrad programs don't assign a mark to these internship accompanying courses. So it's a pass or fail. But no one has failed these presentations before. Obviously, if you don't show up, you fail. But all the presentations in the past were good. And about the timing, I'll also quickly screen share this because there were some questions about the schedule. So we'll have lectures today and tomorrow, both here on campus as well as hybrid. And then you will have some time to think about your seminar presentation. You need to submit your presentation topic via the submission portal here in iLearn. I will send you a notification for the deadline, but the deadline is probably sometime mid of November or something like this, but I'll notify you about the deadline. And in this submission, you just submit your topic as well as the names and student IDs of the 3 to 4 group members, and really 3 to 4, not 2, not 5. And we will have presentations on 2 weekends at the end of November and early December. On Saturday, November 30th, we will have the presentations online via video stream as of 8 a.m., which are from the groups where the majority of students are from the German language AI programs or Künstliche Intelligenz Bachelor. So when you do your submission, you would also submit your degree program where you're from. If it's 2 students from that program and 2 from a different one, I'll just see where I assign you that more or less the days are balanced. If there are too many submissions from that degree program, we would continue on the next day, but my hope is we finish that on that Saturday. Will be purely via Zoom. And the following weekend, it's for the students from the English language program, as well as artificial intelligence bachelors, as well as all other students like exchange students or students from other degree programs. And I'll notify you early in advance about the submission deadline here. You don't need to submit much via this portal, and you will then give your seminar presentation on one of these dates. And I'll, after the submission deadline, I will upload a sheet, and you will see on which day you're finally presenting and all of this. And you will just present in sequence. So the first group in the sheet will present first, then the second group, and so forth. So we can plan this fairly easily. But I expect you to attend all the presentations, at least on the day when you are presenting, because this is also meant to be for you, that you can learn something. So this is the organization. And again, it needs to be more about some management issues and commercialization issues. Your presentation should not be about some purely technical issue. I don't know how to deploy Docker to a certain problem or how to code something and scikit-learn. For this, we have other courses. You can obviously discuss some technical components of your problem when you give your presentation, but it shouldn't be a purely technical presentation, but include commercialization issues. And all the presentations will be online because the reason for the online presentations is, so the course is hybrid today and tomorrow because some students are doing their internship far away. Some are abroad, for example, or in a different part of the country. That's why we do this here on campus as well as hybrid, but I already know if we do the same setting for the presentations, no one will show up. And that's why we do all the presentations online. And it's not my task then that you need to, ask for exceptions and all of this. So we just do all the presentations online. But my hope is that today more students and tomorrow will be on campus for the discussions and also to see our visitors from industry that are giving presentations today and tomorrow. Now there's what I noticed when I started my professorship here 4.5 years ago. We had very technical courses in our curriculum. There were some business-related courses like the Introduction to Business and this kind of stuff, or a course related to entrepreneurship, but there wasn't really anything about business and AI specifically and how to commercialize AI. And I saw there was a lack of such courses all over the world, that either you had very technical courses, or you maybe had some courses that provided more like a business or more like an AI introduction to business students. So extremely technical courses or AI introductions to business students. But what I wanted to see is actually, you have very technical skills, and I want to help you to turn this into commercialization. And there wasn't really anything around the globe when I searched on the internet, and then I felt we should create that course. And we need some literature that is obviously relevant for further reading. Just when I started my professorship, actually my first book appeared, which is called Innovative Technologies for Market Leadership. And in that book, I also wrote a chapter about innovation management for AI. So how to actually make money out of AI, what companies need to pay attention to. We use that as one of the resources. Then in this course, we will obviously look at commercialization, but we look a bit broader also what happens around the globe. For example, in China, the impact of AI on the economy and so forth. And there's a very good book that appeared years before. It's called AI Superpowers. We'll also talk about this book, specifically to discuss how China is involved in AI, because I also keep traveling to China quite often, and I have some deals there as well. So I'll share some insights about China. So this book from Kei-Fu Lee is super helpful. And there's another book that just appeared, I think 1.5 or 2 years ago. It's called Data Science in Context. It's a very helpful hands-on book on business development around AI and what you need to do in order to commercialize AI, how to structure use cases. And one of the authors is Peter Norvig, who wrote this very famous AI book, AI, A Modern Approach. This book appeared, as I said, 1.5 or 2 years ago. And this year, I've integrated some of the content of this book into this course. The book appeared in 2022, and the AI Superpowers appeared in 2018. Now, if you look at last year's recordings, they're not on YouTube, but they're still in my Nextcloud. This course has changed actually quite a lot this year. So I've massively restructured the course, because some topics, in particular these contemporary challenges, have been growing a lot in the last few years, and it got more and more. And eventually all these legal concerns around AI have developed. So I moved AI and law to a separate chapter. I've added some more recent developments around AI regulation. And in this book from Peter Norvig, I found some interesting best practices, something that is called a data science analysis rubric, which is a very helpful approach to structure a data science problem. I've added this, as well as some other approaches. I've added some impressions from China. And every year in January, there's the annual meeting of the World Economy Forum in Davos, which you know from the news. I was in Davos this year in January. And I've also added some of my impressions, what I saw there, because AI was the topic in Davos this year. And I want to share some of my insights from Davos. And I've added plenty of other additions. So the course has actually changed quite a lot and grown bigger this year. And I want to start or continue with a question. I want to know, how is AI changing your life personally? So how is AI affecting you? You're studying AI. You're working on AI, you're using AI as an end user. So it's a very open question. How is AI changing your life? Yeah.
ChatGPT, the voice function, kind of to structure my thoughts, to code, and brainstorm.
Okay. So I'm just repeating it because maybe it didn't appear the recording. One student uses ChatGPT to structure thoughts and so forth, right? We got some answers here in the chat. One student says AI helps in programming. Yes, it helps massively. One student says to get some quick information. One student asks AI when dealing with new programming languages and writing professional letters. Yes, so it can help you in your daily life as well as with coding, for example. One student says AI, eventually you can call AI search engines on steroids, if you wish, yes. So all of us use AI hundreds of times a day as an end user, because it's far more than ChatGPT. We have so much AI integrated in our phones nowadays, or all sorts of online services. I just got a new car during the summer break, which has lots of semi-autonomous driving features, which work quite well. I didn't pick a fully autonomous or some Tesla car. I bought a different one, but it still has plenty of semi-autonomous driving features. So it's actually just sitting in the car and somehow touching from time to time the steering wheel, and the car drives me here, which is quite impressive. And there's lots of AI obviously included. And I like the new car a lot. Also, that a dead angle is not an issue anymore because there's now a camera looking into the dead angle, plus AI checking if there are some objects in your dead angle. So it's really cool. And that car drives me more or less almost autonomously here to work. Thanks to AI. So I'm very happy about this feature. One student asks if programming is almost dead because of AI. We can discuss this here. Do you think programming is dead because of AI? Maybe we do an online vote online, thumbs up if you think AI is almost dead because, programming is almost dead because of AI, or thumbs down if you disagree. What do you think here in the room or the ones online? Any guess or any insights? Is programming almost dead or not? Probably not. I don't think so at all, but I think it just gives you extra productivity. And we need probably even more coders in the future because of all the ongoing digitalization, and the AI can massively support us, and maybe we can work at a more abstract level. So this could be a huge opportunity. And it will save you lots of routine work. So that's what we also just saw here in the chat. One student says AI makes many tasks easier, which makes work more efficient, and coders are still needed. Yes. So I think just productivity goes up massively, but we will later in this course or tomorrow also see how AI is changing jobs and what you need to do in order to adopt, because even you as an AI expert, you are impacted by AI. So you need to wonder how you can actually stay competitive. There is another question here, but it has probably been partially answered by some of you already before when I asked AI seems to work, what could be some downsides? But I want to elaborate on this and ask you if you have any examples of successful or unsuccessful AI projects or transformations in mind. So something that you heard that really worked out, or something that really failed over the years. Or maybe at the company where you're interning right now, maybe they have some really cool AI or something really didn't work out. As well as here in the chat, if whatever you have, please let us know. And there's one comment here just for the past question. And one student says, we cannot hold AI responsible for anything in comparison to humans. Yes, that's true. We cannot really hold the AI responsible, but there are people building the AI. So what are some examples of how AI has really worked in some use cases, or where it has really failed? I'll see if anyone has something. For the ones who are joining online, you can also just turn on your mic and tell us some story if you wish. In the meantime, I'll say something. I remember this was probably like 10 or 15 years ago or something. There was a teenage girl, and she received like letters, I think from Walmart, or ads what a pregnant woman should buy. It was a teenage girl, and the dad complained to Walmart, and Walmart apologized. And a few weeks later, it turned out she was actually pregnant. So the AI noticed this just based on other stuff that she bought in the early pregnancy. Maybe she wanted to eat some special food, drink some special drinks, without knowing that she was pregnant. But the AI had found some underlying pattern, and then sent ads for stuff targeting pregnant women. So I don't know if you heard that story. It was some 10 or 15 years ago or something. Or AI has been used to create new burger sauces, new food and stuff like this that people could have never come up with. And now with all this generative AI, we see super interesting arts that no one could have ever come up with, and we can just generate it in seconds. I think this is really cool, but there are obviously also some downsides or some projects that failed. And I think often all of this has to do with just totally wrong expectations, especially by managers who don't have a background in AI. And I see this too. So when I worked in industry, but also now when I do management consulting, when I go to companies, sometimes they tell me they want to do AI, and I ask, so what exactly is it that you want to do with AI? That you say we want to do AI. And what you're doing then is you're starting with a solution, and you are not only looking for problems, but you may be creating problems that had not actually existed in the first place. And then if I continue asking, so what is it that you want to do? They say, yeah, we have some data set here. I want to do AI. And I say, yeah, it doesn't work that way. And sometimes they say, well, the AI should figure out what we could actually do with that data set. I don't know if you've had such discussions during your internship or if you have seen something like this, but this often has to do with a total lack of understanding. And then I first of all explain what AI is, what it can help us to do, and when it's really helpful. But as a decision maker, you still need a certain goal that you want to achieve. And then you have to solve it as simple as possible. AI may be the solution. Sometimes it's not the solution. One student says the biggest fail is that most UIs right now have a giant button for AI assistant, even for software as simple as PDF viewer. Maybe true, yes. So that could also be some AI washing to some extent, because everything now seems to be AI. But since I didn't get as many responses as I wanted, we will do a breakout for, say, 10 to 15 minutes, and I will all move you in a few breakout groups in Zoom, maybe like 10 students per group, and I just want to discuss for like 10 minutes or 15 minutes or search a bit about some very positive examples and some very negative examples of how AI has worked out. And we can then discuss this. And here in the room, you can also form groups, and we'll also pause the recording, and we are back in 10 to 15 minutes. So welcome back from the breakout sessions. One student wrote before the breakout sessions that AlphaFold is a huge success, yes, which was also part of the Nobel Prize in Chemistry just recently. One student says companies use AI just for the sake of using it. Okay. What are some of the results of your breakout groups now? Maybe if you're online, raise your hand and I'll call you then if you want to share some of the results from your discussion. Or here in the room, have you found any very good or any very, really bad examples? Yes?
Especially board games, there are lots of AI companies and projects which try to develop AI to play those games, like AlphaGo or Starfish.
Okay.
Which are working quite well.
Okay, board games. Yes, AI is super helpful. Any other examples? Also, again, for the ones online, you've had your breakout sessions, and I guess you have discussed something. So if you want to share some of those results, just raise your hand, please, in Zoom, and I'll call you then. One successful example, Devin got millions from investors, but was just exposed as a GPT wrapper. Yes, when ChatGPT appeared, there were all these wrappers around it. Like, for example, just to upload a PDF or something. So someone built a super simple web portal in which you just upload a PDF, run PDF to text, and put a text into a ChatGPT call. Super simple. And once ChatGPT started to offer this on their own, that startup obviously disappeared. There was no need for it anymore. AI art has been developing significantly. even hands problems is solved. Maybe you can elaborate what you mean by that problem. I guess like manual work. So so now it actively pushes back the work of real actors, real creators and editors. Yes. So it's changing jobs. I've had such discussions too. Like I was a few months ago at a summit or at a conference at a military university, concretely the one in Munich, and we debated also about how AI is changing jobs, and I said something, yeah, well, it's changing jobs of creators and editors. The AI is automating this now, so you need to adopt, and I said from a macroeconomic perspective, it's a huge opportunity because it eventually reduces inefficiencies in the market, because now you have the AI, so those people could do other work. And someone was super angry at me then when I said this and said, yeah, what shall these people do now? And I said, well, maybe work in care or something, in old people's homes. And that made that person even more angry. But eventually there we have less automation. And also if you as a coder don't use AI, you will also be out of business sooner or later, because your competitors could be even your friendly classmates or your friendly colleague at the desk next to you. If they use it and you don't use it, you're out of business sooner or later. So you need to adopt. Another unsuccessful example is stability AI. The student writes that their CEO promised there wouldn't be any programmers in the next 5 years. And that company is not profitable yet, and the CEO stepped down. Yeah, those are just totally exaggerated claims. We will also see some past claims as well as some new claims. And those claims, they have consequences, and we'll discuss them. So thanks for all these insights. Is anyone still in here in the classroom that wants to share something from the discussions? We'll do more of these breakout sessions today, because I don't just want you to sit there and wait for this day to be over, but rather I want you to engage. There are some lists of selected AI failures, so feel free to follow these links and see them, and there are obviously many more on blogs and so forth. You can already starting today, think about your case study, because today you're either on campus or online, because you need to find a group. So talk to others. We also have the forum in the iLearn course. So you can use that forum in order to form groups if you wish. You can pick a company you've been working at or any other company, whatever you wish. And there are lots of other examples online you could find for your case study. And you would then identify these challenges when implementing AI, as I said, more from a management perspective, not too much from a technical perspective. And you would explain how you would address these challenges. Yeah, this was the introduction, so you know what all of this in this course is about. And we will start a bit now with history of AI. You have probably had a quick intro to the history of AI in your introduction to AI course. Did you have something like this? And we will not discuss in detail the history of AI, rather some historic promises. And maybe a revision if you have taken the intro to AI, but we have lots of other students from other programs and exchange students. So it will also provide them with some new insights. So the field of AI all goes back to, as a research field, to the proposal from 1955, a proposal for the Dartmouth Summer Research Project on AI. Who of you has ever read that document? Maybe raise your hand if you have ever read the document in AI, or raise your hands here in Zoom if you have ever read it. Because a lot of courses refer to it, but many people have not actually read this document. So In 1955, the people who worked on AI at that time, they didn't call it AI, but they wanted to meet in the following year, so at 56 at the Dartmouth College at the East Coast of the US. And they wanted to have a summer seminar or summer research project, whatever, to work together. So they needed funding. So they wrote a proposal in 55, and they called that field they were working on AI. Obviously, there are works from AI that had existed already at that time, and there are works that go back to earlier days, like the 30s, 40s, or even longer. So they had to write a proposal, and in that proposal, they wrote what they wanted to investigate. So they wondered, for example, how a computer could be programmed to work with language. They discussed neural networks, how machines could self-improve, and a couple of other things. And they wrote this in order to get their funding. So the original document looked something like this. And their belief was that all of that would be solved during the next summer, and then the field of AI is over or solved. It wasn't that easy, obviously, because things like working with natural language is not anywhere close to being solved, but we've made progress. And I think that's a super important document, but it created a lot of expectations. So you largely read, or what you largely find is this proposal on the internet, or it's referred to in the literature, but you don't find much about the outcomes of that conference, because there was some progress, but obviously those problems didn't get solved anywhere near. And there's a question, when did the field of AI really start? Obviously, there are works from before 1955 that nowadays are also mentioned in typical AI literature. For example, the Checkers program from 51, the Turing test from 50, early neural networks from the 1940s, the famous book L'Homme Machine from 1747, as well as the Turk from 1770. Who knows what the Turk was? Yeah.
Turned out it wasn't really a machine, it was more a person who was hiding inside of the machine.
Yes, so we got the right answer both here in the classroom as well as in the chat. This claimed to be a machine, or it was claimed that that machine could play chess, but in fact, there was a human inside it playing chess, so it was a fake. And this is called the Turk, and there's this very famous portal from Amazon, the Amazon Mechanical Turk. I don't know if you know this portal. You can use this if you need some data labeled, and it's obviously not done by a machine, but by people who work in low-wage countries, and they label the data for you. So if you ever need data labeled, give a try at the Amazon Mechanical Turk, which just refers to this because it's not done by the AI, but rather by humans, usually in low-wage countries. So these are some works on AI from before 1955. And those works, as well as this conference, this started to spread a lot of optimism around the field of AI from the late 1950s to the early 1970s. And sometimes when I give keynotes or speeches all over the globe, I often ask people in the beginning, how old is the field of AI? And some people, they think, yeah, it's 5 years old or from the 90s. And there's definitely a small minority of people who guess right that it's like the 50s or 60s. Sometimes there's obviously someone in the room who knows 55, 56, but a lot of people think it just started. And even today, some people don't know what AI is, what that word means. So obviously it's something that we cannot believe because we work on AI all day long. But I remember like last year, I got gas in the night for my car and I paid, and I have my club membership of the ADAC to get 1 cent off. And I gave this club membership to the staff, and it mentions my full name, so Professor Dr. Patrick Lerner. And then the staff asked me, so you're a professor in what? And I said, AI. And the guy asked, what is that? And that guy is maybe 45 or something, you know, not like, you know, 90 years old. I said, well, AI in German. He said he had never heard about that. And I said, yeah, but you don't watch TV or you don't read newspapers. And he said, no, I don't care. You know, I just work here and then I go out or something like this. And then I don't know, I had to stay 15 minutes because it was night, so there were not any other customers. And the guy wanted to know what AI actually is. And I told him about, you know, the Terminator and this kind of stuff. And that started to ring a bell slowly. So there are still people today out there, they have never heard about AI. Even so, but the field is not new at all. And there are now some quotes that I want to share with you, say from a publication from 1958 that claimed something like that within 10 years, a digital computer would be the world's chess champion. This was proposed in the late 50s. Has this happened within 10 years? So were there chess computers in the late 60s that could beat the best human players? Yeah. Yes, IBM only achieved this in the 90s when Kasparov was defeated. And we got the right answer here in the chat as well. No, so this did not happen, at least not that quickly. It took 40 years approximately rather than 10 years. And that paper also claimed that within 10 years, a digital computer would be able to discover and prove an important new mathematical theorem. This is also possible nowadays, and it's been happening, but probably not within those 10 years from that time. So there was a lot of optimism that AI would make massive progress within just a few years, but there were lots of limitations. Simon said in 1965 that machines would be capable within 20 years of doing any work a man could do. Today we would say any work a human could do. Has this happened within 20 years? Not at all. Then Minsky said in 67 that within a generation, the problem of creating AI would be substantially solved. Now it's more than 1 generation since then, probably almost 2 generations, and it hasn't been solved or not substantially solved at all. We've made progress building AI. And then Minsky said that from 3 to 8 years, we will have a machine with the general intelligence of an average human being. This has also not happened. And we are not there yet and probably still quite far away. But we'll talk about the topic of artificial general intelligence later. But there are consequences. So there are very high expectations if you make such claims. This leads, first of all, to lots of funding from government and from industry, but there are high expectations. And there were challenges in the 1970s, so 50s to 70s, like limited computer power. And at some point, researchers also started to understand that a lot of these problems would lead to combinatorial explosions. So you would have just an exponential amount of instances you would need to look into. And for that, even super fast computers are not necessarily a solution. So these were some of the challenges, but first of all, limited computer power, probably also limited understanding of these problems. And there were more challenges in the 70s that you have here for further reading if you wish. But one of the challenges was that you would need to describe common sense knowledge and reasoning, how humans do this. This was attempted in the 70s for a long time using expert systems. And I forgot the name, but there's some guy, I think he's trying to build an expert system for the last 30 or 40 years to solve every problem in the world, and they still keep working on this expert system. I forgot the name, but you can find it on the internet, and they always keep saying, well, we are still working on it, because they try to describe common sense, knowledge, and our whole environment. This doesn't work. And there are some more challenges for further reading if you wish. Then neural networks were already mentioned early on in this proposal for the work at Dartmouth College. Neural networks was already in. At that time, they didn't build any proper networks, but all they had were just single neurons they tried to build in a computer. So what we would call like a perceptron, or later a logistic regression. These were simple units, and only later they started to build networks out of this, probably as of the 60s and 70s. And this perceptron model, it was introduced concretely in 1958, but there were obviously earlier works on neural nets, also from the 40s, but the perceptron was described in 58. And that's why nowadays we talk often or sometimes about a multi-layer perceptron, an MLP. This is sometimes a different word that we use for a neural network, because you have a layer of perceptrons. Even though nowadays we don't use perceptrons, but we use logistic regression units in a neural network. And then there was this famous book in 1996 called Perceptrons, and it showed a very severe limitations of what perceptrons could do. Does anyone know what that limit, or first of all, who knows what a perceptron is? So you've learned that in your AI courses. Does anyone know what the limitation of a perceptron is? Yeah. Yes, only linearly separable problems. And which is the typical data set that it fails on? Yeah, maybe a simpler one, just with 4 instances. Yes, the XOR problem. So the XOR data set cannot be linearly separated. And this was extensively discussed in this book, Perceptrons. And somehow this book, Perceptrons, it had maybe a negative tone, but it was also, I think, largely misunderstood. And the consequence was then, or the belief, that even if you have multiple of these perceptrons, not just one, but multiple, that such a construct wouldn't be powerful either. And this led to lots of problems eventually, but there were other claims. In 1958, the New York Times reported, so I have the screenshot here of the article, new Navy device learns by doing. Psychologist shows embryo of computer design to read and grow visor. The Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious about its existence. Was that really available in 58? Still not available today, at least the reproduction part. Nowadays, we have very powerful AIs that can maybe generate speech, do vision, write text, maybe control some robot. But certainly such stuff was not possible in 58. And yeah, one consequence of this book, Perceptrons, was probably also largely a misunderstanding of the book, that the understanding was that those constructs were not powerful. So a lot of researchers lost interest in neural networks. But if you have a multi-layer perceptron, so you have multiple layers of these perceptrons and you combine them, this in fact can become super powerful and separate nonlinear data sets. So today we talk more about neural nets or deep learning because we use more like logistic regression units, not perceptron units. And the field of neural networks is sometimes also called connectionism in the literature. And that criticism in that time largely targeted not just perceptrons, but connectionism as a whole. Now, we saw high expectations, but little return because there were high claims initially. And then something happened that was called the first AI winter. Since there were all these critiques, at some point funding stopped because a lot of these promises were not kept. And when funding is cut, there is less research, less staff hired at universities, and so forth. And this AI winter, at least in the English-speaking world, often is something like denoted from 74 to 80, but depending on where you look around the globe, this may have been slightly shifted or extended. Then in the 1980s, suddenly there was another boom. Again, funding. Do you know why in the early 80s there was suddenly a huge boom or also funding for AI, especially in the US? Yeah. Yes, because Reagan was elected and then massively advanced R&D in defense. And there was lots of funding through DARPA available for AI. There was a big rise of expert systems as well as of connectionism. And in that time, plenty of interesting applications were created, like chess computers, optical character recognition, autonomous driving, and lots of other things work to some extent. Not as good as they do today, but there was lots of progress. And also progress in methodology. For example, the work of Hinton and others on backpropagation was heavily used here then. And Hinton also just got the Nobel Prize in physics a few weeks ago. And there was also an increased popularization of AI in everyday life. For example, I looked up the first Terminator movie was from '84. But there were, again, lots of expectations. There were some results, but probably, again, too many promises that were, again, not kept, which, again, led to major cuts to research funding. And that area is often called the second AI winter, again, with varying dates in the literature, but something from around 87 to 93, depending on where you look at. So, ups and downs all the time. But then something happened in the early 90s that has really changed it, because, say, as of the mid-50s to the late 80s, most of that work was in academia. Maybe towards the 80s with more applications in industry, but still limited. So it was largely an academic discipline. And the term AI had a very negative connotation, say, especially during this time around the second AI winter. And I had read once a LinkedIn post a few years ago. There was a lady, she said she had finished her PhD sometime during that second AI winter in the US. And she was looking for professorships, and she was even advised to delete the term AI altogether from her CV. So it seemed to be negative to get hired as a professor in that time. Now it's just the opposite. Now everyone wants to do AI, but she had done her PhD in AI. She was even advised to remove AI from the CV altogether and just, refer to computer science. Yeah. But then in the early 90s, the World Wide Web started to spread massively. And suddenly much more data was available. So that's helpful. But also computing time became much cheaper as of the early 90s. And AI started to be integrated in larger systems, like in industrial robotics, logistics, speech recognition, banking software, medical diagnosis, also web search. So we not just had data through the web, but also AI became a fundamental or integral part of web search. So what we saw as of the early 90s to around 2011, much more use cases in industry. Still far less than today, but there was progress. And there are some super popular examples from that time, like you mentioned already when we discussed when the first chess computer started to beat the best human players. And this was concretely in 97. In May, Deep Blue bet Kasparov, who was the worldwide leading chess player at the time. And then the field of autonomous driving also made progress. Concretely, in 2005, there was a Stanford robot that won the DARPA Grand Challenge. Do you all know what DARPA is? So DARPA is an agency that is connected to the US Department of Defense, and their task is to invest early in new technologies and to help ramp up technologies and use cases, provide funding for startups or industry, obviously always with the goal to use it for military later. And DARPA hosted this grand challenge in 2005, and a Stanford robot won it and drove autonomously a 131-mile-long road or path, mainly through the desert, and won it. There was a previous DARPA Grand Challenge, which was 1 or 2 years before, which was much shorter, and none of the teams succeeded. All of the autonomous cars crashed and none won it, which was a big disaster, like 2003, 2004. But then there was lots of progress, and the Stanford team won it. And the person behind this is actually a German person, Sebastian Thrun, who was a professor at Stanford at that time. And he was the lead person of the team that won the DARPA Grand Challenge. And now there's been lots of progress, obviously, in the last 20 years with autonomous driving. And there are also, obviously, military applications. So I think the early investments from DARPA finally have probably worked out quite well. There were, over those years, also various predictions around AI. So in 1968, 2 researchers that imagined that by the year 2001, there would be a machine with an intelligence that could be matched or exceeded, or that would match or exceed the capability of human beings. Has not happened yet, and it still has not happened with ChatGPT. So it was probably a prediction that was very... First of all, they thought it's more than 30 years away, but it didn't work out. And there were some questions around that time then why this has not worked out. And Minsky, one of the AI pioneers, believed the answer was there were like central problems like common sense reasoning were neglected. And most researchers pursued other things like commercial applications of neural networks. There was also a hype for genetic algorithms at some point. And that he believed that common sense reasoning was excluded. There were other predictions, or there are other predictions, like Ray Kurzweil. He wrote this book, The Singularity is Near. So the singularity would be the point of time when we achieve machines with human-level intelligence as a whole. He has predicted that we would achieve this by 2029. In one of the later chapters, we'll talk about the singularity in greater detail, and we'll discuss if this is actually realistic. And others have argued that neural network research ignores essential properties of how the human brain works because we prefer simple models that are maybe loosely inspired by the human brain in order to solve simple problems. This has been argued, and so forth. We'll see how all of this develops, but this was now one of the historic views. And what we have seen is lots of promises, but also lots of setbacks. Now we're in a new era, the deep learning era. Do you think, before we look at the deep learning area, that we are on our way towards a new AI winter? Yes?
personally, I think if there aren't any big innovations regarding like LLMs and things like that in the next few years, that it could happen because a lot more people seem to see the limits.
Okay.
Models.
So you say there are limits for LLMs and we need something new in the coming years.
Yeah.
Okay. Are there any comments from the students online? You can also just turn on your microphone or send a text via the chat if you think that there is a new AI winter coming or not, or here in the classroom. Well, I personally think there are lots of promises around AI. Some of them are realistic, and there are lots of unrealistic ones that, like, AI would solve all your problems. LLMs, they are super powerful, but they have their limitations. And I think if we build ever larger LLMs that just need more data and more electricity, this will probably not be helpful either. But I don't think that we will run into a new AI winter. There will be, as usual, probably some normalization, that some startups disappear or some branches, but we've seen lots of commercialization now, even though the fail rate is high, but this is often the same for newer technologies. But we see that there's much more adaptation of AI in industry and not just in research. And that's why I don't think there will be an AI winter. We'll now discuss a little bit more the deep learning era. We'll see some breakthroughs, what has happened, but again, some promises and hypes. And we try to put all of this into context to see if we're actually on our way to a new winter or not. But we'll see various promises and hypes. And then I think we've done the historic part to look more into AI transformations, contemporary problems, and law. But we'll have a break now and for 15 minutes and continue then. So welcome back from the break. And now that we looked at the history until around 2010, 2011, we'll look at the era we're in now, and that's what I often refer to as the deep learning era. So deep learning goes back all to connectionism, neural networks, and a neural network is something that our AI students have come across in multiple courses, I guess, but we have more students here from other degree programs or exchange students. So in a neural network, I have at the very left the input units, at the very right the output units. And what I want to do is I want to map from the input to the output. And I have so-called hidden layers in between. And I can have one hidden layer, I can have multiple hidden layers. And all these connections between these units, these are the weights or parameters of the model. And when I train the neural network, I want to determine these numeric values for the connections among the units so that I can map the input to the output and not just do this for the training data, but always with the goal of generalizing so I can still do this well for unseen data. That's the idea of neural networks. And as you saw, they were already mentioned early in this Dartmouth document from the 1950s. This figure is from a famous book in 2006. Does anyone of you read this book for your studies from Bishop, Pattern Recognition and Machine Learning? Maybe thumbs up if anyone has read it, because I refer to it in many of my technical courses, but I don't know if my colleagues refer to the book, say in the machine learning course. Maybe in Zoom, raise your hand or thumbs up if you have read the book. I saw one or two people here. Is anyone using it? So I have to say, this is my absolute favorite machine learning book, Pattern Recognition and Machine Learning from Chris Bishop. I think it provides a very comprehensive and in-detail view of machine learning, but it's a tough read. It's lots of maths. And that's why the book has mixed reviews. Either people love it or people hate it. And sometimes if Bishop derives something, he just skips 5 steps and say, this is easy to follow or something. And in fact, it's not that easy. And I once even saw the website of a professor, I think from MIT, and he wrote on his website he does not recommend the book because he himself doesn't understand it. So it's a tough read, but it's my absolute favorite machine learning book. And obviously, the field of neural networks has evolved since then. And for a long time, a successor book was announced, but no one knew when it would actually appear. And then last year, just before Christmas, a deep learning book by Bishop, exactly the same style of the book appeared for deep learning. And I was lucky enough to get a copy just before Christmas because I spent a few weeks for Christmas in Shanghai, and then I had a chance to take the book with me and read the whole deep learning book during the Christmas break. So I think if you want to get a super good understanding of maths and its details in machine learning by pattern recognition and machine learning, it's a tough read, but super helpful, as well as the successor book on deep learning. And this figure is from the first Bishop book, or from the first one I mentioned. Bishop already did a book on neural networks in the 90s, which provides a very good perspective of neural networks from that time. But the deep learning book is the one that is up to date. So that's what a neural network does. And because we have these units, which we call also neurons, this is called a neural network. And the whole area is called connectionism. But I think a lot of people have a lot of wrong impressions from this. I see a lot of strange stuff on the internet, lots of claims around these neural networks, or other consultants or startups. They say they build an AI that works like the human brain, this kind of stuff. So it does not. And I think when you, as an AI expert, deal with your managers, they may have some of these wrong impressions. So tell them how this stuff works. You can break this down in 5 minutes, at least the essence, and tell them this does not work like the human brain and it's not super intelligent. But there are lots of wrong, lots of misconceptions, and that probably leads to lots of consequences because people think that this really worked like the human brain, and they expect eventually similar results. But nonetheless, the neural networks are super helpful for certain machine learning problems. And they are deep neural networks if you add lots of hidden layers. And in a very good journal paper, or no, it was from, I think, a book or something. Yeah, from a book 10 years ago. There was a very interesting figure in it. And it starts in the 50s, so at the left side on the x-axis, from the 50s to 70s, what it denotes is a perceptron, and then some networks. And then in the 1980s, there's a huge rise of expectations and media hype. And at some point, there's a downside. So this is some sort or something that we called the AI winter before. There are a lot of expectations that couldn't be delivered on, and there's a drop of popularity. But it goes up again. So this is a little bit shifted to maybe the second winter, AI winter, because this specifically addresses neural networks. And these neural networks, they have a very mixed history. I remember people like Yann LeCun. Yann LeCun is one of the most famous deep learning experts and heads AI research at Meta. He described that 15 years ago or 20 years ago, it was so difficult to publish neural network research in machine learning journals, machine learning conferences, because a lot of colleagues believed that neural networks did not work, that they had failed. But we saw in the 80s, there were already some things that worked, like autonomous driving to some extent, optical character recognition. But then there was this drop in popularity because neural networks have some issues, and you've all worked with neural networks. Maybe we can discuss a bit what are some typical issues that you would face when you train a neural network. Any comments?
Overfitting,
yeah, overfitting can be an issue, that they learn the pattern too well and they cannot generalize. Other issues? They may need a lot of training resources when you build large ones. But overfitting is definitely one of those issues. And then in 2006, something happened. A paper was released on how to train deep neural networks efficiently. And that paper was, again, from Hinton. And what he described is something that is nowadays quite normal, that we pre-train a neural network and then we fine-tune it. These terms are now often used in terms of, say, large language models, that you train a large language model from scratch and then everyone can fine-tune it as they wish. But what that Hinton paper proposed in 2006 was, and it was, they actually didn't call it too much a neural network, I think more like some kind of Bayesian network, but it's the same approach, that you pre-train the neural network. And what they did is they pre-trained this neural network layer by layer. So they trained the first hidden layer, then the second hidden layer, always based on the previous layer. And then they had some initial weights that were quite good. And then they fine-tuned with the regular backpropagation. So they didn't try to train it directly with backpropagation, because if you have many hidden layers, and this was already understood in the 80s and 90s, many hidden layers can give you some very powerful advantage, that you can self-learn features in the data, but it tends to overfit because more layers means more parameters. So overfitting. And with that approach, the overfitting was reduced because you first trained layer by layer. And then once you had some initial reasonable weights, you could do the fine-tuning with backpropagation. And that paper in 2006 has led to lots of excitement around neural networks. And this was also then adopted by industry a few years later. And everything we have seen since then, like large language models, generative AI using deep neural networks, all of this would have probably not happened to that extent if that paper was not published in 2006. This approach of first doing pre-training layer by layer and then the fine-tuning, this is not too common anymore, because now we have new approaches like different activation functions, dropout, and lots of other techniques which came up later. But that first paper in 2006 has really led to a big change around neural networks and increased interest. So lots of new methodology was derived. So this was now 18 years ago. And the question 10 years ago in this book was that how all of this would develop. Would it still go up on this hype cycle? Would it go down? Would there be some plateau? And I think what we have seen is it went even far more up in the 10 years than it could be expected 10 years ago. And now we have lots of new stuff like large language models, ChatGPT, and so forth. And deep learning is so interesting, and I'll provide a bit more context on deep learning, because we not only have the students from our AI undergrad programs here, because with a deep neural network, you can obviously learn a pattern that you need in the data, or that you want to find in the data, but you can also self-learn features. So you can train the neural network on the raw data. This is something that you often cannot do with a lot of machine learning models. Like a lot of machine learning models don't work well just on pixel values or just on text. You would need to pre-process your data set and find features or derive features, and then put your machine learning algorithm on these features, but you just don't know which features you need to describe and how. For vision, there are various approaches like edge detectors, whatever, but then which one do you pick and so forth. And deep learning allows us that we can often feed in the raw data. We can, in the first few layers, self-learn features, and in the later layers, we actually do, and typically just in the last few layers, we would actually learn the pattern we are looking for. And this can be visualized very well when it comes to vision. This is from a Google experiment some 10 or 15 years ago, in which they wanted to do something very, very simple, which was quite challenging at that time. They wanted to build an AI that can distinguish whether a human or a cat is in an image. And they didn't know how to do it, and they looked into deep learning for this. And deep learning actually solved the problem quite well. They took those images from YouTube videos, and then once they had trained a neural network and it worked well, they also tried to visualize what the units actually recognize. So for neural networks and vision tasks, you can actually visualize what the units learn, which features. For text and so forth, that's more challenging, but for vision problems, it works super well. And they saw the first few layers, they learn on their own to detect very simple features like edges. Later layers learn to recognize groups of edges. Later layers, groups of groups, and so forth. So you build an increasingly more complex feature hierarchy. And the last few layers to the actual pattern, the actual discrimination. And this has sparked lots of interest because you have other problems aside from vision where you don't really know how to describe the features, like speech recognition, natural language processing, and so forth. And deep learning has been applied to all of this. And there have been some breakthroughs in the last, say, 18 years since that Hinton paper. There are new training methods since that time. So we can reduce the overfitting, we can train faster. We have much bigger data sets available than we had 20 years ago. We can scale the training, for example, on GPUs, a TPU. Who knows what a TPU is? Yeah.
Tensor or tensor processing unit?
Yes.
From Google, right?
Exactly. Tensor processing units. So GPUs are graphics processing units. They're helpful for matrix manipulations, in particular matrix multiplications, additions, which has been used for decades for video games, for the rendering of video games. And most noticed that you can run this, or you can use this hardware to train neural networks, because eventually to train a neural network, you just have matrix operations. But if you look specifically at like convolutional neural networks and some other architectures, you actually don't just deal with matrices, you deal with tensors. So vector or a matrix, they are tensors, but tensors can have more dimensions. And these tensor processing units from Google, they've been popular for such tasks. Or FPGAs. Who knows what an FPGA is? An FPGA is a field programmable gate array. What that means is, so if you build an ASIC, so an application-specific integrated circuit, it's one piece of hardware that does exactly your task. But if you want flexible hardware, you can look into FPGA. So an FPGA is a piece of hardware that can be customized. So it has all sorts of flash cells and connections among these flash cells. And these flash cells, they represent logic functions. And now you could set these flash cells and their connections in a certain way that this piece of hardware does a specific logic function for you. And you could change that setting for a different one. You don't want to manually think about the flash cells, but you would use a hardware description language like, for example, VHDL. With such a hardware description language, you would describe how the hardware works, what it shall do, and then you would have a software package that turns your hardware description into a mapping on the FPGA. So you have flexible hardware and you can just change these settings again if you wish. This is something we will look in a little bit greater detail in my big data course, which many of you will probably take next semester. And FPGA stands for Field Programmable Gate Array. Field means customer. So the one who buys the FPGA can customize it in order for it to represent different logic functions. And FPGAs have been also used successfully for training neural networks. There has been progress with generative adversarial networks in the last few years. Deep reinforcement learning. Some of you mentioned board games before. There's been progress because we can now play board games at superhuman performance with tools like AlphaGo, which combines deep neural networks with reinforcement learning. And then in the last 6 or 7 years, there has been lots of progress around large language models, which in particular go back to the attention mechanism that helps us to find better patterns among text. These large language models are also something we look a little bit more at in my big data course. But all of these breakthroughs have been there for the last 18 years, and it all goes back to one paper that massively sparked interest again in deep learning. And concerning these board games, I also want to say a few more sentences. So there's a company called DeepMind. They were founded in 2010 in London. And what they built was a neural network that can learn on its own how to play video games similar to how humans play video games. And what they did is they fed the video input into the neural network, and the AI could take different actions. For example, move forward, jump up, jump down, move backward. And there was an outcome. The AI succeeded or the AI failed the level. And then the AI learned on its own when to take which action, so when to jump up, forward, and so forth, just based on trying different actions at a time, and then failing or winning the level, and it just looked at the video coming from the game. So that was a breakthrough in that time, and Google eventually bought DeepMind in 2014. Their price was unknown, but estimated somewhere in the range of $400 million to 500 million pounds. And Google advanced this work and was able to integrate this kind of AI in its search engine for specific queries. And essentially what that approach from DeepMind does is you combine, it's a reinforcement learning AI, but rather than, for example, Q-learning or whatever, you use a neural network. And you combine this with a Monte Carlo tree search to efficiently navigate the different actions you could take in your tree. And that approach has been used to play video games, but then it was also applied to the game of Go. And I remember when that AI, AlphaGo, was released, just 9 years ago. This was just at the end of my master's, and everyone was super excited because we just finished our AI degrees, and suddenly AI sparked huge interest because of AlphaGo, in particular in Southeast Asia, where the game of Go is far more popular than here in Europe. Because for chess, superhuman AIs have been built since the late 90s. And for Go, it seemed unlikely to many that that would happen anytime soon, because when you play such board games with an AI, what you need to do is you have a tree of actions. So it means you take now this action, then your challenger takes the other action, you could take again an action. So, and you need to look ahead in this tree for multiple steps to see what could happen in order to take the most likely action. There are AIs, or there are algorithms to do this for a very long time. For example, like the min-max algorithm or alpha-beta pruning, which have been described in AI books for many decades. You all took the programming 2 course. In the past, I taught a programming 2 course, and I covered the min-max and the alpha-beta pruning algorithm there. I don't know who teaches the programming 2 course now. Does he cover this stuff or different stuff? Louder? Okay, good, because when I taught the course, this was part of one of the mandatory assignments, but then someone else teaches the courses and obviously changes the content. So the challenge is you need to look ahead many steps because you want to take the right action now. But it's a combinatorial explosion of steps because you cannot just look 50 steps ahead. This doesn't work. Say if it average, you or your challenger could take dozens or hundreds of different actions. And for Go, you can take much more actions or much more possible actions at a time than with chess, because the board is much more complex and you could move around or you could do much more actions than in chess. And this made it effectively difficult to build an AI that can look far ahead in the number of steps and then choose the supposed right one. But with DeepMind and its AI AlphaGo, this was solved in October 2015 and became the first computer Go program to beat a professional Go player on a 19x19 board. This has sparked huge interest in AI, and obviously this work has been continued and extensions of that have been applied to AlphaFold, for example, for protein folding, and many other examples. So there has been progress in this deep learning era. But there are also some concerns. Say, if you now take a large language model and you want to train it from scratch, and these numbers were just from a few years ago up to GPT-2, you could see that it already could cost tens of thousands or hundreds of thousands of dollars just to train a model. So there was a transformer from 2019, and just training it from scratch would require you 656,000 kilowatt hours, and the compute cost in the US at price levels at that time was somewhere around $1 to $3 million. Now the transformer models are much bigger. Electricity, at least in Europe, has become ever more expensive. So that's also a concern. And training these models is super expensive. You need a lot of electricity. And what I feel is a lot of people are using the LLMs for tasks when they actually could be using simpler models. Obviously, LLMs are helpful if you need to answer complex questions, you need to summarize complex texts. But if you just want to classify a text into a language, say, is this text in German, is this text in English, you can just use a naive Bayes or some other simple machine learning model to learn to do this much faster, much cheaper, maybe even much better. So that's something I'm worried about. And I think you need to pay attention to this too when you work as a data scientist in industry. You need to know when to pick which tools. So don't always just pick an LLM or a neural network for every possible task. Always think about how you can solve this as simple as possible. And I have a few guidelines later for you on how to do this. So rising energy costs are a concern. And some people say, well, AI can help us to work on climate change because we can become more sustainable. But if we need ever more electricity to train AI, we could maybe create the opposite. And this, now I have a few slides that are maybe more to, to entertain you a bit, because we've talked about this before, and some of you had mentioned it in the chat that some people are not AI experts, but they claim they are. This creates lots of issues, lots of wrong expectations. There's the saying here, like a vampire doesn't like sunlight, Superman doesn't like kryptonite, and data scientists don't like research and math. And there's, these are just some mock-ups from LinkedIn, yet they are funny. So there was this claim that Microsoft uses AI to make Windows 10 updates smoother. And maybe this is actually not AI, but just some simple rules. And obviously it jokes. So if the user is doing stuff and has unsaved work, then you should be doing the update. So sometimes simple things are reprinted as AI, again, a term that is often referred to as AI washing. Or something like this, maybe at a hackathon, a team won and they claim that they used machine learning to greet the user with a personalized message. Maybe it's just this, that you put in your name and then you're greeted hello with your name. So a lot of things that are now rebranded as AI are often not that trivial. And this is something you also see quite often, that people have super high training accuracies and then validation or test accuracies are super low. A sign of what? Overfitting. Yeah. Massive problem. And then I'll give you a little bit of time to look at this. So this was from the Harvard Business Review. It's an example of how to plot data skills on a 2x2 learning matrix. Some skills are considered not useful, very useful, time-consuming to acquire, or not time-consuming to acquire. And I want you again to discuss this in a breakout session where you actually agree, where you disagree, and we'll continue in a couple of minutes. So welcome back from your breakout sessions. So you're all welcome to share your insights, where you agree, where you disagree. Yes?
Was like statistics as being the one almost closest to being ignored or something.
Yeah.
But I guess it's more of like abstract statistics rather than just generally knowing, because up in the middle there's statistical programming, and I guess the combination of using statistics for programming is more useful. I will put statistics higher.
Yeah, so the statistics one also confused me because it's certainly super important, and somehow statistical programming is more important than statistics. Like you argued, maybe this is higher, but it still needs statistics. Good. Is there some point where you maybe agree? Also, for the ones online, I want you to engage in the discussion. Yeah.
For me, I like the data science as being the highest one.
Okay.
Yeah, just because I want to be a data scientist, so it's
yeah.
Yeah.
Well, I think most of this sheet has confused me, or most of this matrix, because somehow data science is more important than machine learning, but machine learning is needed for that. Data cleansing seems to be not useful, but data cleansing is super helpful, because if you don't clean your data, it's just garbage in, garbage out. And well, maybe acquiring skills in business intelligence is less time consuming than in machine learning. Yes, but also data cleansing takes a lot of time to learn in order to do it right, because you need to do an EDA, an exploratory data analysis, which isn't that straightforward. So lots of confusion, I think, here. When this appeared on the internet a few years ago, got lots of negative comments. And remember, it appeared in the Harvard Business Review. So if it appears there, people believe this, and there are consequences. And then maybe some executive would say, we don't need to spend time and budget on data cleansing. It's not useful, and you don't need to know statistics. You can do your data science directly. So there are consequences. And don't trust this stuff if it appears even at a top journal like Harvard Business Review, because it's not necessarily correct. But this was a big thing on LinkedIn a few years ago. And now I also sometimes put in some LinkedIn posts, and I've removed the name and the face of these people, because it's not to put blame on anyone. It's just to engage in a discussion. But if there's something where I totally agree, sometimes I just keep the name and the face. But for maybe other more critical parts, I just remove their name and faces, because it's not to blame. It's just for a discussion. But one person here found a paper on the internet, or some thesis project about combining AI and blockchain. And the poster here says that this thesis offers a brief overview about how AI could be used to deliver bug-free smart contracts to achieve a certain goal of the blockchain. What do you think? We can use AI to deliver bug-free smart contracts. Does this sound promising or not? Well, we'll do another quick breakout session. So you can think about in the breakout session what bug-free means and if AI can help for this. So welcome back. We got the first question here in the chat, and one student asks, what is a smart contract? Who of you knows what a smart contract is? I thought all you guys are into blockchain and all of this stuff, you know. So maybe you can raise or like thumbs up if you know what a smart contract is, or if you at least have a little bit of an understanding of this. Well, please. Yeah. Again? Okay, yeah.
Smart contract is kind of protocol on, I don't know, how to store transactions or like verify that the transaction is true, or like something happened or something.
Yeah. Well, yeah, so one guy here wrote in the chat, where the crypto pros, you know? So we got one green sign for that. So the one who just sent a positive response about or whoever feels they want to share with us what a smart contract is, maybe just turn on your mic and tell us. Don't be shy, just tell us.
Like I don't know much about it, but I only know a little bit that the smart contract is like it's your ID, and then from the other user can pass on it. It's like something like that. Maybe I'm not 100% correct.
Okay, well, a beginning. So thank you. We have another green response. Please turn on your mic and tell us then.
All right. So a smart contract is an executable code that is it's like an application running on this blockchain where the application can be used to handle transactions or to to govern it. It's like a backend for a crypto application.
Yeah, fine. Yeah, thank you. So yeah, it's some sort of automation for a blockchain, and it is an automation of a contract. So if certain rules are true, something will happen, but it isn't necessarily smart, you know, it's just a simple automation. So I think, again, the term smart contract to me largely means like AI washing, I don't know. So when I've talked to some of those crypto pros, they said, oh, it's all smart. It's not necessarily smart. Maybe you add something smart, but it's just some automation. Now we know what a smart contract is. And here, someone wants to use AI to deliver bug-free smart contracts. And I think if I remember this document correctly, they used an AI to generate tests or something. So can we use testing to show a program is bug-free? Not at all. So Dijkstra said, you can use program testing only to show the presence of bugs, but never the absence. So program testing, you can show bugs, but if there are no errors in your test, that doesn't mean it's bug-free, because maybe you just missed writing some test that could expose it. So for showing bug-freeness, you need to do formal verification and this kind of stuff, which is tricky. And what was used here was some machine learning to deliver or to write some tests or something. And in machine learning, again, you have uncertainty because of the statistics. So that approach is not necessary, or it isn't one that will help you to deliver bug freeness. But when someone posts this on LinkedIn, especially a CEO of a company or whatever, you know, people believe that. It's not to blame, it's just a discussion. And I think if you want to deliver on AI very well, you still need a very good understanding of computer science. Because AI is very interdisciplinary, and that's important. We need people from statistics, from economics, from all sorts of domains. But for the in-depth methodology, it's still super helpful if you have a background in computer science, in software development, in algorithms and data structures, because then you know these things and understand these claims. Then this one here appeared, which was posted by McKinsey, so big consulting firm, claims to be the leading one in the world. And they posted, or one of their leaders posted something like machine learning versus deep learning. So, and it was compared, and somehow you could conclude from that that deep learning was better than machine learning. What do you think about that? Yeah. Exactly. Deep learning is one branch of machine learning, nothing more, not a separate discipline. But again, if people post this, people start to believe that. Or again, from McKinsey, they wrote something like, this was a post, I think it got deleted later because it got too much criticism. And McKinsey seriously posted that unlike other types of machine learning, reinforcement learning uses algorithms. Is that correct? Not at all. I mean, all computer science is about algorithms. And in order to do supervised learning, you need algorithms. But if this comes from a big consulting firm that charges lots of money per hour, maybe customers think, yeah, this is not really what I need, you know. It's just 3 disciplines, nothing else. And for all of them, you need algorithms. So this is just to provide you with a little bit of an overview in this very exciting AI world about lots of hypes. And unfortunately, this leads to consequences if people really follow such advice. This one here, and it's just some joke about consulting, how you can make a career in consulting. There was once a guy, he posted, he worked at McKinsey as an associate, and his task was to make pretty slides fast. Then he got promoted to engagement manager, and his task was to make other people make pretty slides fast. And then he got promoted to associate partner, and his task was to convince clients pretty slides will lead to real impact. And I think that's something you see largely in strategy consulting, just nice slides that don't mean anything, but people pay enormous amounts. So, you know, when I worked in industry, so I worked at Krones Group. Krones Group is the worldwide leading manufacturer in bottling lines. And every second bottle here in Central Europe is filled by a Krones line. Worldwide, 1 out of 4 bottles. And I was in charge of AI at Krones. And when I started there, yeah, more than 6 years ago, around 6 years ago, there were obviously people who had explored AI there before, because my task was to build an AI team for a corporate AI team. And others had obviously done some prototypes before, and one manager did a project with a large consulting firm about some data set. But all they got was finally, they paid 50,000 euros and they got 20 slides that didn't mean anything. They paid 50,000 euros and the consulting firm looked into the data set, and the results were just nothing, you know, just some few plots and something, and you couldn't derive any business from that. And it was 50,000 euros, you know. And and there were no consequences. And I mean, with 50,000 euros, you can pay maybe a data scientist for half a year if you look at the full cost, salary plus other costs. Or you could hire, I don't know, 2 or 3 interns for 1 year, and they certainly will deliver more on that. So, and I'm not against consulting at all. I do a lot of consulting through my own consulting business, which is very helpful for me because I get to see real world use cases and keep my connections to the real world. And these are insights I can share here as well, aside from obviously the considerable financial impact. Consulting is important, but there's also lots of bullshit consulting, like people that just create slides or talk nonsense. And working in consulting is a great opportunity. So I just remember 1 or 2 people here in the online sessions that they were doing the internship in consulting. If you want to see a lot of different use cases and meet lots of different people, the best thing you can do after you graduate is here work in consulting for a few years. And there are very good consulting firms that do AI very well and not just slides. And probably this will be a huge impact to your future career if you work in consulting, because you get to see lots of different companies, lots of different projects. It's tough work, and you'll work 60 hours or more per week, and you'll be traveling all the time. Probably now, after COVID, less than 10 years ago, but you get to see a lot of different people, and you get to see lots of different domains. And then maybe after a few years, you can switch to one of your customers. So if you can do a career in consulting, it's probably super helpful, at least for the beginning of your career. And then if you like this, maybe you'll advance to partner, which is a tough life. And probably if you become partner, this will guarantee you a divorce at some point because you're just married to your work, But you can also switch to a customer at some point. And I also worked in the consulting business. So just before I started my professorship, I got a job in a consulting company too. Probably Germany's leading AI consulting company. And I was the manager or the manager in charge of all the training business. So they did consulting, but also training sessions. And I was in charge of the business unit for trainings. But I just started there. And then a few weeks later, I got my offer for the professorship. And then I was still there for 2 months until the professorship started. And I saw lots of customers because I not just did the training things with my team, but also was involved in projects, advising customers. And it was a great experience, good pay, but tough workload. And I knew I would get the professorship then. And then I told my wife that this was probably the best paid consulting internship ever, because I ran the business on trainings, was involved in projects, had a good pay, but I knew I would leave and get a professorship here and then start my own consulting business. But it paid very well. But consulting is tough. Don't underestimate this. So I'll share a few more insights because, it's an innovation management course and some of you will end up in consulting. In consulting, so before COVID, your work looked like you're with a customer Mondays to Thursdays, and typically on Fridays, you're in the office for trainings, discussion with your colleagues, and some extra work. Now, after COVID, it's changed. You're also doing more remote consulting. You're not spending 4 days per week with your customer, which is very helpful if you want to have more of a life. Obviously, there's still plenty of customers that expect you to be on site, and certain things need to be on site. But there is, in most consulting companies, usually there's daily reporting. So what matters is you get your salary, and you need to have as many chargeable hours as possible. So you need to track your whole day and charge as many hours as possible on a specific project, on one project or multiple projects, which will then be billed by the consulting company to your customers. And there's daily reporting. Before we saw this one here, and I heard one student asked, what's business intelligence? I think someone wondered what business intelligence is. when I followed your discussions. Business intelligence means you're doing reporting from data. You're not doing like forecasting, for which you would use things like machine learning, but rather you would look at report, or you would generate reports from your data. And typically in a consulting firm for your direct manager, he or she will do daily reporting and see how much of your time got charged or not. And the expectations, at least until COVID was, so you're 4 days with a customer, 1 day in the office, which is often work that cannot be charged. So if you're fully charged, this means you could charge 80% of your time, but a lot of consulting firms usually expected that at least 85 to 90% of your time gets charged. That means more work Mondays to Thursdays. And then Monday and Thursday, you would sit in a train or plane, because you would go to the customer typically on Monday, return on Thursday. And that's, if you sit in a train, you may be able to work. If you sit in a plane, not necessarily. And you still expect to work very hard. You're expected to work very hard. So doing consulting is tough, but it's very rewarding. You get to see lots of customers, and you can stay in nice hotels and all of this, you know. So it's also fun. Or if you have some, you know, maybe more, say, top-level advisory, this would maybe happen in nice 5-star resorts, 3-star Michelin restaurants, and this kind of stuff. It's fun, you know. Maybe not as a junior, but as you evolve, you will get involved in that kind of consulting. But there were also certain times I was maybe 3 times per week in a Michelin restaurant, and all I wanted was just to sleep at home in my own bed, you know. So I've also been through those times. And I'm not keen to go to another. There are still Michelin restaurants for consulting from time, but I don't need that anymore. I've been through that. That's why I think, but if you have a chance to do consulting, after you graduate, do it. It's tough, but you don't have kids yet and all of this, so you have less obligations, and you can certainly speed up your career and then maybe switch to a customer, maybe to one of your customers as a team leader or something like this, and could certainly be helpful. And once you work for the customer, maybe it's a little bit less pressure, because I don't know if you work at an automotive company, you don't need to do daily reporting through a business intelligence systems to see how your hours are chargeable. But then it's not just you who need daily reporting, it's also the managers who have daily reporting, because their manager will also look into the numbers of the people below him or her. So the pressure is on everyone. And if you advance, you can obviously become a partner in certain companies, so you can get small piece of the ownership, to which you need to contribute financially a lot. So a lot of people becoming partner, they need a loan in order to get shares, but you would typically first become an associate partner or salary partner. Only later you would become an equity partner. And then you're involved, you will get a share of the revenue, of the profit, whatever. But that's a tough job. And as I said, most people that I know that made it to partner in big firms, they had at least one divorce, probably more. So, because you're really married to their work. Yeah, and there's daily reporting for everyone except maybe the top CEO. So it's a tough job, and what the managers in a consulting firm need to do a few times per week, at least once per week, sometimes more often, are staffing meetings. So a staffing meeting would mean the managers sit together, they look at the projects that need to be worked on in the coming week or weeks. They would discuss which consultant would be on which project. So you as the consultant, you're not fully involved in the choice which projects you get to work on. Obviously, you are asked at some point, but this kind of stuff is typically decided in a staffing meeting where the managers sit together and discuss, we have this project, we need these skills, or this person is maybe not yet at 90% chargeable, so we need to put him or her maybe 10 more hours per week on this project. So it's tough life, daily reporting, something you will not face at many other jobs. Okay? If you work as a coder, maybe you have a daily Scrum meeting or something, but it doesn't mean necessarily that this gets charged directly to someone like every hour. Maybe rather your customer would pay towards a contract and whatever. So consulting is tough, but great opportunity. So who of you feels now that you want to be doing consulting after this? Maybe, and if you're online, maybe just raise your hand. Thumbs up. It's tough, but it's fun. And I started in that consulting company, and a few weeks later, I knew I would get my professorship. But I saw this as a manager because I was in charge of all the training business. And that was really cool. And I told my wife it's the best paid consulting internship ever, because it came with big pay. And I knew I would see 3 months how consulting works and then start here and then start my own business. Yeah, and it's being recorded, but it will appear on YouTube. But I'm still friends with the owner of that consulting company because he understood I got my appointment to professor. And we just had a phone call 2 or 3 days ago. So it's all fine. And consulting has high, there are lots of people coming and leaving in consulting. It's not like you spend 10 years with the same employer. Most people maybe work 2 years with a consulting company and then they switch to a different one or switch to a customer. So it's extremely volatile. So hope you all got some, was this some new input for you about consulting? Like some things you didn't know? Good. There are obviously lots of other tasks like sales and all of this, but this is typically something that's like when you start as an associate, you're not involved in sales. You would start with work, coding, or slides, whatever. And the more you advance, the less the technical skills, and is actually because the more you advance, you need to deal with clients, you need to do sales, you need to look into profits. So this becomes more and more important, and this is when you get to sit more and more in Michelin restaurants and nice 5-star hotels, which is also fun. But consulting is never an 8 to 5 job or a 9 to 5 job, whatever. So it doesn't work that way. Yeah, and so this is some insights about consulting, and there are some other blog posts on the internet like this. You don't need maths for machine learning. I guess we've talked about this enough, but some people really believe this and write blog posts, and then some managers read this. Then we'll come to something that I think I also discussed this in my big data course, but this is a different course here, so we'll talk about this. So for the last 20 years or so, there has been there have been different directions in machine learning. And there's often a sentence, it's like or 2 sentences. It's not really a quote, but it's something that was often derived as a consequence from a paper. And there was a paper in 2001 that's called Scaling to Very, Very Large Corpora for Natural Language Disambiguation. And this paper is probably one of the most important natural language processing papers from the last few decades. Corpora that were called or considered very, very large at that time are now probably medium size because a lot has changed. But what they did in that one was to compare different algorithms about how they could classify language. And something they noticed is that the exact algorithm didn't matter too much. Rather, if you simply put in more data, then the results got far better than picking a different algorithm. Obviously, some algorithms worked better than others. And that's why sometimes the summary is something like it's not who has the best algorithm that wins, it's who has the most data. But now in recent years, we've seen transformer models, which also make a huge difference. Now, the question is deep learning always the right choice? Because deep learning has allowed to skyrocket various applications of machine learning. Is deep learning generally better than other methods? Thumbs up, like raise your hand if you think it is, or thumbs up here in the chat. I got a question here in the chat if there's any company I can recommend for consulting. Well, as a civil servant, I have to be neutral and I'm not allowed to recommend. Obviously, if you work at places like McKinsey, they have super big impact, maybe not that much technical work or less, but you can check my CV or LinkedIn and you see where I worked. And those kind of companies, they are more hands-on. Obviously, they do slides, but also deliver on real problems. So I still want to know from you, raise your hand or thumbs up if you think deep learning is always the right choice. I see one green sticker. Now maybe raise your hand or thumbs down in Zoom if you disagree, if you don't think that deep learning is always the right choice. Yeah, and that's correct. I've already given you some hints before. I said maybe if we just have, we want to classify some text, we can do this very well with a naive Bayes. We don't need an LLM. But there's also some theory about that. And there is something called a no free lunch theorem. Who has heard about this before? Okay. Was this in the machine learning course or where did you see it? The no free lunch theorem says that no machine learning model is generally better than others for all possible problems. And therefore, as a consequence, we need to assess multiple models on a data set. And I got another question here about the consulting. If there is a book that I can recommend, there is, I forgot his name, but there's a very famous author who wrote dozens of books on consulting. Maybe just send me an email. I'll look up what his name is. I have the book at home. He provides probably some quite good advice on consulting. So just send me an email or I'll send me an email and I'll prepare it and I'll show maybe briefly tomorrow what that author is called if you want to start in consulting. So as a consequence of the no free lunch theorem, we need to assess multiple models on a data set. And this goes back to a paper that appeared around 30 years ago by Mr. Wolpert. And what he wrote is a paper that is called The Lack of A Priori Distinctions Between Learning Algorithms. And what he derived is the no free lunch theorem. There are actually two no free lunch theorems in the literature, one on optimization algorithms, one on machine learning. Here we refer to the machine learning one. And what he said is, imagine you have some specific supervised learning problem. Let's say supervised simplified for now. Some data set. And you have all the supervised models you could imagine, different neural networks, naive Bayes, decision trees. What would you notice if you run all these models on one data set? What would you see in the results? What would most likely happen? Just one data set and all the possible models. You would see that some models do better than others because for one data set, you've all seen it. Maybe a neural network does better than a naive Bayes or the decision tree does the best. But now imagine not just one problem, one data set, but all possible data sets and all possible models. You will see some models do better than others in certain problems, but they do worse in others. And it can be shown that in average, all these models perform exactly the same throughout these problems. Some obviously better than others in specific problems, but they will do worse on other problems. So in average, they all perform exactly as good. There's a theoretical proof for that, and there are various papers, numerous studies from the last decades that have shown empirical evidence that this is really the case. So there's some papers, they find 100 different, classification algorithms and 100 different data sets, and they run it all. And they see, obviously, some do better than others on some problems, but in average, for example, the accuracy is exactly the same. What does that mean? That doesn't mean that you don't need to care about the model. You still need to care about the model because this no free lunch theorem also, it's theoretical and it's correct, but maybe there are certain data sets, certain problems that hardly appear in the real world. Maybe there are certain problems that appear more often in the real world. And for those, certain models tend to work better than others in average. Now, what do you need to do? So over all these years, I try to come up with a few best practices. Actually, I created this slide deck, I think, or these few slides here, already some 6 or 7 years ago, when I tried to just summarize how I would solve some, say, for example, supervised machine learning problem and how to pick the right model. Don't just start training first a neural network. This will not work. And when I review, for example, papers for journals or conferences, what I often see is nowadays, or for the last 5 years or something, that they have a data set and they train a neural network and they say, this is how it works, we're done. Such a paper typically gets rejected because maybe the neural network was not necessary at all. Maybe you could have solved this much easier in the first place. Maybe some other model works far better. And don't start with the training of the model. You need to do a couple of preliminary checks. You need to understand your data. And that's something that is often called EDA, exploratory data analysis, where you do visualizations of your data, you calculate some summary statistics, you would check maybe if there are lots of missing values, impossible values. We look at this stuff in detail in my big data course. You would then also maybe check for biases. Biases in data are also something you will see next semester in the big data course. And based from that data, once you have done some cleaning, maybe you could try to build some simple features, what you could maybe derive from the data. Maybe you skip sometimes that step of building features and you just continue with the raw data. Sometimes not. Then you would have a simple baseline model, maybe some linear model, say maybe a logistic regression for classification or a linear regression for regression or something like this. And usually this would be very easy to train and you'll get some output and you see overall how good or how bad it works. And maybe here you can already stop. Maybe your model gives you 99% accuracy. And from your business problem, maybe 95% is just enough, you can stop. Then, if you're not good enough yet, you can try to find the right model. And there is this figure here. It comes from scikit-learn. Has anyone ever seen this? So it's on the scikit-learn website. It's from a few years ago, and some people say now scikit-learn is much bigger. That's true. Yet it can give you some orientation what to do. So you have some problem. First of all, you need to figure out, is it a regression problem, classification problem, or some unsupervised problem like clustering or dimensionality reduction. And then you can go through this and you can find a model that could be quite helpful for your task. You train the model, you see how it does. Does it do better than your very simple baseline from before? If it does better, well done. If it doesn't do better, maybe you stop here, but maybe this is also a sign that there's some issue in the data. So maybe you need to go back to your first step, like understand your data. Maybe there's just some strange bias or whatever. Now, if we say it's, for example, still a supervised problem, say a classification problem, we could try to build a different model. And something that has been shown in the literature is that random forests or variations thereof, like gradient boosted trees, whatever, they work quite well on many real-world problems. Is this something you have also witnessed over all these years, that these tree models, especially like random forests, gradient boosted trees, they give you quite a good baseline on many real-world problems? If you've noticed this, maybe thumbs up, hands up. Obviously not for all problems, but for some, or for many, they overall give you quite good results. And there are some papers to address this. This is not a violation of the no free lunch theorem, because the no free lunch theorem says for all possible problems, but there are probably also impossible problems or problems that rarely appear. And for real problems, these random forests, they work empirically, typically quite okay. Now you could stop and say, maybe I'm fine here, and you can use random forests for both classification as well as regression. But you can also continue, and you can say, well, I could try now lots of different models, or I use something like AutoML, automated machine learning. Who of you has ever used anything like this? I've mentioned it briefly in the computer vision course in the context of convolutional neural networks. Maybe you remember this. And what you can do is, well, I don't want to be trying all these different models, say now for some classification task. Rather, I let my computer try this. And there's not just like 100 different models. There's other things like pre-processing of the data set. Do the features need to get normalized? Which hyperparameters, and how do I optimize the hyperparameters, like the depth of the tree, or in a neural, or not neural networks yet, or maybe the learning rate, this kind of stuff. And rather than trying this on your own, you can let AutoML, automated machine learning systems, let that try for you. So it's just a little bit of code with a library that is called AutoSKLearn. And this library will not naively try every possible model and every possible pre-processing step. Rather, it will start with a few of them. And internally, it will use some machine learning algorithm itself to quickly find you something helpful that works for your data set. That you maybe need 100 trials or less, and then you get something quite useful. So this is something you should definitely be trying. It will speed up your work, and you don't need days to write lots of code to try all these different models. Maybe AutoSKLearn or some of its competitors will just do this much faster for you and maybe much better. So it's something you should definitely be using. And once you have done this and you're still not happy with your results, maybe give a shot at deep learning. Obviously, if you have some very complex natural language processing problem or some very special vision problem, maybe you should try deep learning a little bit earlier in these steps. But don't start with deep learning. This is my advice, because deep learning is helpful, but it comes with lots of costs, lots of complexity, and not necessarily better results. So bear in mind these steps. So first of all, understand your data, clean your data, build features if necessary, a simple baseline, choose a different estimator if possible, try random forests, or eventually try AutoML, and eventually try deep learning. So these are some of my best practices that I have come up with after all these years. We got a question here in the chat about the consulting book, and the student will send an email. So, welcome back from the break. What we have done so far today is we had the introduction and saw what this course is about and the overall issues or challenges when you try to commercialize AI. Like most projects seem to fail. We've seen the history with lots of promises, lots of hypes that has led to 2 AI winters. I don't think there will be a 3rd AI winter, because now in the deep learning area, we have massive commercialization of AI. And if you pick the right people and the right use cases, you can succeed quite well with AI. And this is something we will look into in this chapter. Like some general things you need to look at and that you need to bear in mind when you deploy or when you want to advance AI in a company. We'll look at opportunities, challenges, and best practices. And then after lunch, we'll have a guest lecture. And later in that lecture, maybe today or tomorrow, we see more contemporary challenges, in particular, legal challenges that have come up in the last few years. So, one question that I often face is, especially so when I do executive advisory, what is AI? And you all study AI, but others are totally confused by AI because everyone uses different terms. Some people talk about data science, some talk about AI, machine learning. And how would you define AI? I want to hear this from you. What would be your personal definition of AI? Yeah?
Automated predicting based on previous data.
Based on previous data would mean we're tied to machine learning, but there are other approaches too. But a good first attempt. Yeah.
So maybe algorithms which can change themselves based on the data they receive, so they're not static.
Okay. But if we have an expert system, it could be static and still fall into the category. So you see, and we'll ask here online, is there anyone who wants to share his or her AI definition with us? If so, maybe just raise your hand in Zoom and then turn on your mic. So we see it's difficult. And there's like this saying, like you have 2 lawyers and 3 opinions, and it's probably the same. You ask me and my colleagues, and we all disagree. And that's a huge problem to others, like your potential customers or executives, because if even the experts disagree, then how can we actually convince someone else that we are doing AI? And there are some challenges because AI massively overlaps with other fields. So there's a huge intersection with statistics, a huge intersection with signal processing, with logic. And I've seen people over these years, like one professor that I know personally, he said, well, AI is just like statistics to him, just the same thing. Or machine learning is the same as statistics. And here I would disagree because in statistics, we aim to infer some properties of a data set. And maybe we have some hypothesis that we want to reject or not. But in statistics, we aim to infer some properties from the data set. But in machine learning, we try to predict for unseen data. So we want to find a pattern, but this is not the actual goal. The goal is to predict on unseen data well. We can use machine learning, we can use statistics for this, but there are other approaches in machine learning as well that have nothing to do with statistics. For example, you can do logic learning, learning of finite automata. So machine learning is much more than just statistics. There's obviously a large majority of models in which we employ statistics, but with a different purpose than what we would do in statistics. So when I sit together with executives, I say, well, AI allows us to automate human decision-making. This is like one sentence how I at least can get the attention of an executive. And what I say is humans make up to 30,000 decisions every day. There are studies that show these numbers, and these decisions can be in private life, like driving a car, when to choose when to drink a coffee, what you do with your kids and so forth, but also in professional life, like setting prices, writing code, controlling some equipment. and so forth. So lots of different tasks for which we need to decide. And the way I see AI is we want to automate that decision making. And that automation means something totally different than automation, say, in a factory, because in a factory, we have automation since the beginning of the Industrial Revolution, which was all about automating physical tasks. Because humans are really bad in doing the same physical behavior over and over again. Like, I don't know, just do whatever physical task you can do in a factory, like filling a bottle or bending something, whatever. We're not good in repeating that because we get tired and quality drops. And that's why the Industrial Revolution came up more than 200 years ago to do exactly this. And now we have robots in factories. But AI mainly targets at what humans are good in, which is making decisions all day long. So it's a totally different goal. And there are different directions we can take. We can take expert systems, logic-based approaches, or learning. So this is how I would define it and explain it to a decision maker. But someone else may disagree and define it differently. This is fine. But it does confuse others that we as AI experts don't agree about what AI is about. Everyone has a different definition. And I mentioned before Peter Norvig, who is one of the authors of these books, Data Science in Context. Peter Norvig is largely famous for his book, AI, A Modern Approach, that he wrote together with Stuart Russell. So who of you uses that book for studying AI, A Modern Approach? Maybe hands up if you've looked into it or not. You guys, you should be looking into that literature because these are so I expect more of you to look into these books because they are the essential literature in AI. And Peter Norvig is one of the authors of AI, A Modern Approach. Stuart Russell is the other author. And I met Stuart Russell earlier this year in Davos when I was at the big meeting during that week of the World Economy Forum. And I asked him how he would define AI personally, because he's, I'm a big fan of his book. And I had a 1-hour chat with him in Davos. And he himself struggled to adequately define it in 1 or 2 sentences, which is perfectly fine because the field is vague and intersects with lots of other fields. And I asked him if they had attempted to provide a definition of what AI means to them in the book, but he also struggled with that. He said if they put in a definition and someone would criticize, it would just, come on that and say, well, we would define it differently. That's why even in a leading AI book, they don't attempt to define AI. This will all cause lots of trouble when we look at AI and law tomorrow, because there are now all these wishes to regulate AI. And if you regulate something, you need a legal definition for it, which will severely complicate all of that. So what I suggested then to Stuart Russell was for the next edition of his book, and I'm a big fan of AI, A Modern Approach. I said, maybe if they are scared to define it, I understand it, but maybe they could look at definitions of others and analyze and assess them. Maybe this could be a beginning. And then you could say, well, we define AI and say it has different sections. One of them is machine learning. How do you define machine learning? Again, you see, it's not just you say AI is expert systems and machine learning. Then your legal definition is not done because you need to define the other subcategories as well. So we see it's complex, but that's what I suggested to Stuart Russell, to look at definitions of others and to assess them. And maybe this could be an introductory text in their book. Now, when you want to deploy AI in a company, there are essentially 2 directions you can take. One direction is that you put AI in the value chain of your company. Value chain means the internal processes. So things like HR, procurement, sales, R&D, whatever. This is all your value chain. You can try to put AI in there to automate certain internal processes. So you're more efficient, you reduce costs and all of this. This is one direction. A different direction would be that you put AI in your products or services. So you help your customers to optimize their value chain using AI. What do you think, which direction is probably the one that is a little bit easier, value chain or product services? Louder? So products, okay. Let's see who answers in the chat. Mixed reviews in the chat. So we'll try. So everyone is listening here. We have lots of people in the chat. I want you to vote with green if you think it's the value chain, or red if you think it's product, services, these kind of things. And we have 60 people in the chat. I'd like to see a lot of responses. And here, maybe raise your hand briefly if you think it's value chain, 1%, or if you think it's products or services. Okay. So strong. So there's a strong majority for products and services. And also here in the chat. From my experience, actually, the value chain is the easier one. They are both tough. It's not easy, obviously. But when you access your value chain, you have access to the people in the company. You hopefully have access to your data and IT systems. I know there can be all sorts of challenges like data silos and legacy systems, but you can easily try out stuff internally or more easily. If you put AI in your products or services, you run into lots of additional issues. First of all, you need to sell it to your customer that they are willing to buy AI or pay even more for it. I know when you do a project internally, it will also create costs. But when you do an R&D project for products or services, it will also create costs. But you need to somehow maybe charge your customer or convince of this. Then there's obviously regulation if you use AI internally, but if you use AI externally, there's lots of extra regulation. Like we will see this in AI and law, like the Digital Services Act, Digital Market Act, product liability. And another thing you should never underestimate when you sell something like products or whatever, there could be the issue of patents. So if you try to sell a new product on a market and someone has a patent, you cannot just sell it, you know. Theoretically, you are also not allowed to build and use something internally if there is already a patent on this. But if it's internally, you would say it's a trade secret. No one would really know you're doing this. So it's awfully difficult in such a situation for an external stakeholder to enforce a patent for what you're doing internally, because it's a trade secret. You're not revealing it. So both directions are difficult, but from my experience, the value chain is the one that is a little bit easier and faster because you don't need marketing and sales and product liability. Rather, you can try to speed up something internally. But whatever direction you take, there's this alarm, I guess, from outside. It's a fire station, I guess. I heard some of our students are actually involved in a fire station. I don't know if anyone here from our department, but I think that's really cool. But your course obviously gets interrupted then. Yeah, so one thing you need to be able to assess, whatever direction you take, whether it's the value chain internally or externally for products or services, you need to be able to assess how good or how bad you are right now. So you need KPIs, key performance indicators or metrics in order to measure something. Say you have a factory and you produce some metal parts and then you have a quality inspection. And there, maybe you can right now measure that 99% of your output is fine and 1% of the output is not fine, and you will melt it. But something I've noticed throughout all these years, also when dealing with companies here through the university or through private consulting, a lot of companies struggle to assess how good or how bad they are in certain processes. And there's maybe some gut feeling or something. And if you're unable to assess this, the AI will not help you at all. You can invest in AI, but maybe you become better, maybe worse, you don't know. You need proper KPIs before you start investing in a different solution. And that's something that is often forgotten, often not considered when doing consulting or when companies start AI projects, and finally they burn a lot of money and maybe it leads to worse outcomes or no one knows. So start with the KPIs. This is not easy. There can be simple KPIs like waiting times, cost, but sometimes it's much more complex metrics. And I've seen this. And like one of my colleagues when I worked at Kronos, bottling line company, that guy worked before for a competitor of Tetra Pak. So you all know Tetra Pak, where you put milk. And there, it's not just the company called Tetra Pak, they have competitors. But for now, just say Tetra Pak, because even though it's not that company, but that kind of container. And he worked for one of their competitors, if I recall correctly, and he said something like, he was the head of R&D there of the competitor, if I recall. And he said something like, they struggled, so they had like 5 experts or something to assess whether a Tetra Pak was clued properly or not. So there are all sorts of ways how you could clue this together, you know, and how to spread the clue. If you spread too much clue, it's not good, it gets too heavy, not sustainable. Maybe some clue goes inside, which isn't great at all when you then put in maybe some hot beverage. If it's not enough clue, it may fall apart. And how to spread the clue. And they said that their domain experts totally disagreed about proper cluing and bad cluing, even though they've been doing this all their life. Like we AI experts disagree about what AI is. And then he said they built an AI and the AI did super well. And this confused me because the ground truth didn't look good at all. Because the ground truth is the experts disagree. And then I said, yeah, but how come the AI did so well? He said, yeah, it did super well and far better than most of the domain experts. And then I said, yeah, how did you collect the data? He said, yeah, the different experts, but one was super ambitious and contributed most of the labels. And I said, well, your AI has learned his pattern, or her pattern, I think, guy, but not necessarily the ground truth. And this is just garbage in, garbage out. The AI system will not necessarily lead to any additional value here. So when you have domain experts disagreeing, you first of all, you need to collect high quality data and bring these domain experts together. And maybe they need to discuss for a while what the label should look like, but maybe they will come eventually to some conclusion. This is how you need to collect the data. You need to have multiple experts label them, and not just draw most of the labels from one expert, because eventually you're just learning what that one expert did. So these are some examples of KPIs, and I've seen this many times in industry that the experts largely disagree about what is correct and what is not correct, or what is good, what is not that good. And you need to reach a consensus first, otherwise you're investing in AI, but it's unclear if it would lead to anything. And that's why I also have this Tetra Pak example here. Again, it's not that company, just a competitor, but referring to this kind of container. So which metric or KPI should you use when? There can be business metrics, obviously, like waiting time, cost, maybe in a cleansing process, how well you have cleaned a bottle or not. But there could be other metrics as well. Maybe how much acid have you used? Maybe you want to reduce the amount of acid to clean something, but you still want your container to be clean. And getting these labels is sometimes super expensive. I know maybe assessing, you know, if some clues are fine, costs you a few euros if experts look at. But I've seen other cases where the labels are expensive. So I did my PhD thesis in detecting electricity theft. So electricity theft is a huge issue in emerging markets when people manipulate their meter or transformers or any kind of other infrastructure with the goal of getting electricity for free. If you steal from your neighbor, this doesn't matter in that use case because then it goes through the neighbor's meter. But if you want, if we define this as manipulating meters or infrastructure, that the usage of electricity is not recorded. That's electricity theft. And I talk about this use case in greater detail in the big data course. But if you build a machine learning system, so we wanted to infer from usage and certain master data, like where does the customer live, what kind of customer, what meter, because some meters are easier to manipulate than others. And inspection labels. So a part of the customer got inspected, and then we want to learn for all customers whether they steal or not. But you need to inspect enough customers, and this was in one state of Brazil where there were, I think, a few million meters with that one utility. And they carried out, I think, more than 500,000, 700,000 inspections or something. The numbers are in my thesis. I don't remember the exact number. But if you carry out 500,000 inspections and you need to send 2 people to a building, they need to drive there and so forth. And this was in Brazil. The utility said the average cost of an inspection is $100 US. So you need to invest $50 million US just in these labels. And these labels are not necessarily correct because maybe the meter inspector got bribed or threatened. If you inspect in a favela or in a police station that steals electricity theft, all of this happens in Brazil, that police stations steal electricity. And if you inspect there, maybe you're not reporting the ground truth. So the labels may be wrong too. And still, the utility had to invest $50 million up front. It's that expensive because you need 2 trained technicians to drive somewhere, and they can do a few inspections per day. They need to drive somewhere, take notes. If there are legal consequences, it also needs to be documented well. So all of this costs money. And I've once advised a company, they wanted to know whether a liquid is in a specific chemical process, if it's sprayable or not. So some liquids can be sprayed well, others not. And this was for, I'm not saying which industry, I'm not able to reveal it, just describing a use case a little bit. They want to know, is it expensive or is it easy or difficult or average to spray a specific liquid? And they had to build an experiment for this, for each liquid, which was insanely expensive. I think thousands or tens of thousands of euros per liquid to measure this, because a very special chemical process. And they did this for maybe 100 liquids as candidates, but they had more candidates, maybe about 1,000 liquids they wanted to assess for this process, which they couldn't pay, obviously, because they already spent lots of money on just doing it. It was, I think, even less, maybe 80 liquids for which they could spray. And they had each time build a super expensive experiment. And they want to know for all the candidates whether they could be helpful for this chemical process or not. And this is how I came in private consulting. And what we did is they could measure other properties of the liquids fairly easy, like the density of the liquid, if it transmits electricity, some other properties, easy properties of liquids you can easily measure with much simpler experiments. And that was done for all 1,000 candidate liquids. And then we could build an AI and learn from the few liquids that were actually sprayed and tested in the experiment. And we try to predict from the other properties of the liquid that could be easily measured. We try to build a supervised learning system that can then predict whether sprayable, okay, or not that great, and not sprayable. And this system could then be applied to all the other liquids, and we predicted whether they are sprayable or not. And the few that looked super promising, then the actual physical experiment was carried out. So saved lots of time, lots of money. So getting labels is expensive, and even getting one label can be in the range of thousands, tens of thousands, or if you look at maybe some protein folding or some, I don't know, vaccines, maybe even in the range of millions what it could cost just to get a single label. So don't underestimate getting the ground truth. And these are some of the things I have worked on that I wanted to share with you. So the sprayable liquids, electricity theft, and the other story from the Tetra Pak that I didn't work on, but I was told. And there was a heated LinkedIn discussion 1 or 2 years ago about how to pick the right, so-called right metric for a specific business problem. And some people claimed in a post that this is super easy. You should always just use the accuracy, and this one would be fine. But accuracy is not fine if your data set is imbalanced. Some people use the AUC, the area under the curve. What I wrote here is finding the right metric is super challenging in real world projects. The accuracy is often not that useful because often your data set is imbalanced. If this is a classification problem, confusion matrix can be helpful to see more, but maybe for some business problems, even the confusion matrix doesn't help you much because you have some other thing you actually want to optimize, maybe usage of acids or glue or whatever. So not that easy, and something that is totally underestimated in a lot of projects. Here I've also removed a name, but it's just an opinion. The person said, don't waste your time telling me that other metrics are useful, and argue that this was actually not that difficult. Start with the accuracy, the confusion matrix, precision, and recall. But depending on your business problem, precision, recall, whatever, maybe it doesn't mean anything. So in real world projects, it can be far more complex than using these traditional metrics. Sometimes they are obviously helpful. Also for our liquids, for the sprayable liquids, it was a classification problem. It was fine. But for other problems, maybe you need a totally different metric. And then this person here, Valeri, I think he's one of the top AI posters on LinkedIn. Can highly recommend Valeri. He specifically wrote about the AUC, the area under the curve. And it's a metric that is often used in imbalance problems by data scientists, but it's hard to argue to a manager what the AUC actually means and what kind of business value it adds. So it's cool from an academic perspective, but in a business setting, how you can actually earn money out of this AUC score is hard to argue. So it's not bad, but maybe read his whole post in case you're curious about this. It's in the slides. Now, when should you actually look into AI? What I often recommend is solve your problem as simple as possible. So keep it simple. If you can just write 2 or 3 rules to simplify something, then do it. Don't train a neural network then. But there are some criteria when AI is helpful, and then, as usual, start with simple AI models and build increasingly more complex ones. For example, so there are some criteria. The first criteria is when AI can be helpful is if a decision problem takes long. So you have domain experts, and it takes them a long time to decide something, to calculate something, and so forth. Maybe they need days or weeks. And maybe with the AI, we can make the decision in milliseconds. So massive speedups. Costs are another issue. So time contributes to costs, but there can be other factors that contribute to costs. For example, if you use extra resources, like use extra acid, for example, to clean something. So that also contributes to the cost, not just time, but use of other resources. Wrong decisions could also lead to massive costs. So costs is overall a big factor. And then I've told you that domain experts often disagree. And this is where AI can also be helpful in order to reduce the uncertainty and make decisions more uniform. Here, AI can be super helpful as well, just to increase the certainty, or that you make more certain or more uniform decisions. And these are some criteria, but again, solve the problem as simple as possible. There can be more criteria. Maybe there's some decision problem. You just don't know at all how to decide so far with your domain experts. Maybe the data can help you to provide some insights. But I've seen lots of strange wishes were to use AI over all these years. So for example, so you have a decision, you have a business process that is just too complex. So you have a lot of, say, steps in your business process, lots of dependencies in a business process, maybe even a lot of mutual dependencies, then the AI will not get you anywhere. You need to rethink that business process and then put AI on top of it. So human intelligence first, and then the artificial intelligence. Don't do it the other way around, because all these best practices I have just shared, if you don't follow them, that leads to these 87% failure, because you use AI maybe for a problem where it's totally unusable for. Maybe you need to use your human intelligence first. You need to decide if AI is useful or what you actually want to achieve. And it's not like what I said before, here's a data set, let's find out what we can do with it. Maybe the AI can propose something. It doesn't work that way. But some managers believe that. So here, if you follow all of this advice, then your success rate in AI will certainly go up. It will not be 100%, because lots of stuff can go wrong, and sometimes maybe in some problems the data isn't enough or doesn't provide insights, or other things can go wrong. But your success rate will be far higher than if you don't follow this advice. What you should never underestimate when you want to do AI in a company is, the question is, who should do it? In companies, there's a huge chaos in the organization. And what you would often see is AI is spread throughout the organization, which is important because everyone should acquire some understanding of AI. What I always tell companies is everyone from the CEO down to the factory worker should get some understanding of AI. The CEO needs to be able to see whether he or she should invest in AI. And obviously the factory workers, they don't need to become data scientists, but maybe the factory workers, they recognize some potential and say, well, you know, we always put this here in a computer, but actually it's in SAP, but we still scan it somewhere else. And actually we still recalculate this. Couldn't this be inferred from the other data? So they need to be able to recognize some potentials. And even if a factory worker just gets a 20 or 30-minute training on AI for their work, they may be able to recognize some business potentials or some improvements, and then forward this to their team leader, who then forwards it to the responsible person. So everyone should have a little bit of an understanding. And then you obviously need to put AI somewhere in an organization. A concept that has often been used is a so-called AI competence center, which maybe defines an AI strategy for the company and has an AI team. But it's not necessarily the AI boss that does all the AI work, but rather does some of the use cases and then enable other teams to also set up AI practices and start working on AI. Because you have so many software developers or engineers in companies, and maybe if you train them a bit on AI, they can advance it in their own organization. And such an AI competence center can support, can work on some of the use cases, can establish best practices. But you as a data scientist alone, you will not be able to solve all of these AI problems in companies because you lack the domain expertise. So if you go into engineering or chemistry, you lack that knowledge. And I'm just looking if we have a pen here because I want to draw something on the whiteboard, but we don't have this. Just checking. Gone, so I'm unable to draw this right now, but I'll try later after the break. And there's other advice on the internet about, so you have different roles. There's not just a data scientist. A few years ago, maybe 5 to 10 years ago, everyone wanted to hire data scientists. And it looked like you only need data scientists. And data scientists not just come from AI programs. 10 years ago, there were no AI undergrad programs. So some, say, computer scientists turned into data scientists. Some statistics experts turned into data scientists. And data scientists are really good to try out something on a data set and build maybe a prototype. But eventually, you need to put this stuff into production. So it needs to run reliably in an existing or needs to be integrated in an existing infrastructure, run reliably on larger data sets, maybe with continuous input. And this is maybe not the strength of a typical data scientist, especially if that person maybe has a background from statistics and not computer science. So over the years, new roles have come up, like a data engineer. A data engineer also needs some knowledge in data science, but is mainly there for the infrastructure, making sure things run reliably, and maybe not too much for the science, but for things that work eventually. So these are two different roles. And over the years, companies needed to hire more and more data engineers because they said playtime is over. Just building prototypes is over, but we also need to put all of this into production. We still need scientists, but also engineers. And there is all sorts of advice on the internet about these roles, what they could look like. Like one person wrote, data scientists shouldn't need to know Kubernetes. I disagree here. Maybe as a data scientist, you don't need to be an expert in Kubernetes, but at least you need to speak the language of the data engineers. And vice versa, the data engineers maybe don't need to be expert in some super fancy statistical model, but at least they should have some understanding of what you're doing so you're able to communicate. I'm not an expert in Kubernetes either, but at least I know what it is and how to talk about it with the right people. So you as a data scientist, you should know these engineering things to some extent. And if you choose to become a data engineer, you need to know the data science stuff to some extent. So you're just able to work together. And there are lots of other roles, obviously. Now, a few more best practices. There is something really interesting that appeared on the internet 5 to 10 years ago. It's called the machine learning canvas. And this machine learning canvas, I find it super exciting because it can be the very beginning of a data science project. Now imagine you are being tasked with, say in your internship or as a consultant or as a data scientist in a company, you're tasked with a specific data science problem. And you need to structure the problem and build sort of a roadmap. And for this, the machine learning canvas can be super helpful. Because the machine learning canvas starts with the center and it says the value proposition. What is actually the end use of all of this? What kind of value shall this generate? And if someone tells you, let's do some AI, some data science, maybe there's no value proposition and you can kill this altogether, or you think about what kind of value actually you want to propose. Start with that. Then think about next, maybe what's your prediction task? What exactly are you trying to predict? What kind of decisions follow from this? Because maybe your predictive system will directly make the ultimate decision, say maybe in a quality inspection process for cheap parts. Maybe a human needs to make the ultimate decision based on the prediction. So you need to think about this. Is the predictive system's decision or prediction final, or will there be some more complex decision made by a human or some more complex system? If you build these systems, which data sources do you have and how do you collect the data? Do you have different data silos? How do you aggregate this? Do you have sufficient data? Which features do you have in your data set? And how do you build your models? And how do you make these predictions? And can these models actually be deployed? So what's the impact of them? And once it all runs, you're not just typically building a prototype that will run like this forever. You need to monitor it. Maybe there's a stream of training data, or you need to retrain it permanently, or once per year, once per month. How do you monitor if the predictions still make sense, or if there has been maybe a data shift? And all of this should be defined early on in the project, not in great detail in the first day, but at least to some extent. And for this, I personally find this machine learning canvas super helpful. And I can highly advise you to use it for your own projects, not just at work, also here at university. It just helps you to structure the problem, and I think it's a very helpful tool. Now it's 12 o'clock. We'll continue at 1 o'clock, and we'll stop the recording here. After the lunch break in 1 hour, there will be a guest lecture, and I'll see when I continue with my stuff today or tomorrow.